On the night of March 12, 2025, the Atlas Survey Telescope in Hawaii captured a faint smudge of light against the star field of the constellation Centaurus. The object was moving, that much was clear, but what it was, and where it came from, would take weeks to understand. The Atlas system, short for Asteroid Terrestrial Impact Last Alert System, is designed to find dangerous asteroids heading toward Earth. It scans the sky in overlapping tiles, comparing images taken minutes apart. Anything that moves gets flagged. Most of the time, these objects are familiar: main belt asteroids, near-Earth rocks, or periodic comets making their rounds. But this object was different. Within 48 hours, the Minor Planet Center in Cambridge, Massachusetts, issued a provisional designation, 3I 2025 F1 Atlas. The 3I prefix is reserved for interstellar objects visitors from beyond our solar system. Only two had been confirmed before: 1I Oumuamua in 2017 and 2I Borisov in 2019. Now, humanity had detected a third. The discovery alone would have been remarkable. But as follow-up observations began, something strange emerged. The object had a coma, a fuzzy cloud of gas and dust surrounding its nucleus, the hallmark of an active comet. Telescopes around the world confirmed it. 3I Atlas was outgassing. It was releasing material into space, leaving a faint tail that stretched behind it like smoke from a campfire. Comets do this all the time. When a comet approaches the sun, solar radiation heats its icy surface. Frozen gases, water vapor, carbon monoxide, carbon dioxide sublimate directly into gas. This outgassing forms the coma and tail, but there's a side effect. The gas jets act like tiny rocket engines. They push the comet, altering its trajectory. This effect is called non-gravitational acceleration, or NGA. Every active comet shows it. It's measurable, predictable, and well understood. Except 3I Atlas showed no non-gravitational acceleration at all. Think of it this way. Imagine you're standing on a skateboard, holding a water bottle with a small leak. As the water sprays out behind you, the skateboard rolls forward. That's Newton's third law. Every action has an equal and opposite reaction. The leaking water pushes you. Now imagine the water is still leaking, but the skateboard doesn't move, not even a millimeter. That's what astronomers were seeing with 3I Atlas. The object was visibly active. Hubble Space Telescope images showed a glowing coma extending tens of thousands of kilometers. Spectroscopy confirmed the presence of gas molecules, cyanogen, diatomic carbon, even traces of water vapor. The outgassing was real. But the orbit? Perfectly gravitational. No deviation, no push, no measurable NGA. By late April, tracking stations across 3 continents had recorded enough data points to calculate the object's trajectory with high precision. The orbit was hyperbolic proof of interstellar origin. 3I Atlas had entered the solar system from the EI direction of the constellation Eridanus, moving at roughly 29 kilometers per second relative to the Sun. It would reach perihelion, the closest point to the Sun, on October 30th, 2025, at a distance of 1.4 astronomical units. Then it would swing back out, passing within 1.7 astronomical units of Earth in early November, before heading into the depths of space. But here's the puzzle. The orbit was calculated using only gravitational forces. The Sun's gravity, the planet's gravitational tugs, even the subtle perturbations from Jupiter and Saturn. When astronomers added terms for non-gravitational forces, the kind that should be present given the visible outgassing, the fit got worse. The data didn't support any NGA, not even a tiny one. For context, 2I Borisov, the second interstellar object, showed a measurable non-gravitational acceleration of about 3.8 key 10 to 7 meters per second squared. That's incredibly small, about 1/10,000,000th of Earth's surface gravity. But it was there, detectable in the orbital data, consistent with the observed outgassing. Comet Hale-Bopp, one of the brightest comets of the 20th century, had an NGA roughly 10 times larger. Even faint, distant comets show some level of non-gravitational effect when they're active. 3I Atlas, 0. Within the measurement uncertainties, the NGA was indistinguishable from 0. This is not a minor discrepancy. This is a fundamental violation of known physics. If gas is escaping from the object's surface, momentum must be conserved. The object must recoil. There is no way around it. Yet the orbit told a different story. By May, the European Space Agency's optical ground station in Tenerife had joined the observation campaign. So had the Gemini South Telescope in Chile and the Very Large Telescope in the Chilean Andes. Each facility confirmed the same result: visible coma, spectroscopic evidence of outgassing, and an orbit that refused to budge. Some researchers began to wonder if the outgassing was somehow symmetric, perfectly balanced jets firing in all directions, cancelling each other out. But even that wouldn't fully explain it. Comet nuclei are irregularly shaped, rotating, and covered in varied terrain. Jets tend to be localized, erupting from specific vents or fractures. Perfect symmetry would require a level of geometric precision that nature rarely achieves. Others proposed that the object might be surrounded by a shell of material dust grains or debris that absorbed the momentum of the outgassing jets. But infrared observations from the James Webb Space Telescope showed no evidence of such a shell. The coma was diffuse, typical of comet comae, with no dense inner cloud that could act as a buffer. What if the laws of motion themselves are being tested before our eyes? The tension is undeniable. On one side, we have centuries of observational astronomy, thousands of comets studied, all confirming the link between outgassing and orbital perturbations. On the other side, we have 3I Atlas, an object that seems to ignore the rules. As the object moved deeper into the inner solar system, closing the distance to Mars and Earth, the pressure mounted. Observatories allocated more time. Researchers submitted proposals for additional spectroscopy, polarimetry, and high-resolution imaging. The James Webb Space Telescope pointed its infrared sensors at the approaching visitor, searching for clues in the thermal signature. Hubble continued its ultraviolet watch, tracking changes in the coma's brightness and composition. And still, the orbit remained stubbornly Newtonian. The facts are extraordinary enough. An interstellar object, visibly outgassing, with no measurable non-gravitational acceleration. But the implications, those are what keep astronomers awake at night. Because if the outgassing is real, and the orbit is real, then something we don't understand is happening. Either the object has properties we've never encountered before, or there's a mechanism at work that doesn't fit into our current framework. And as 3I Atlas continued its approach, the window to find answers was narrowing. By the end of May, the object was already brighter than magnitude 20 faint, but within reach of professional telescopes. Predictions suggested it would peak near magnitude 16 in late October, possibly visible to dedicated amateur astronomers with large backyard instruments. But the real prize wasn't visual observation. It was data, spectra, photometry, orbital tracking. Every night mattered. The countdown had begun, and the mystery deepened with each passing week. To understand why 3I Atlas is so baffling, we need to step back and look at the broader context of interstellar objects. These are visitors from other star systems, travelers that have wandered through the galaxy for millions or billions of years before crossing paths with our sun. They're rare, or at least detecting them is rare. And each one teaches us something about the universe beyond our immediate neighborhood. The first confirmed interstellar object, 1I Oumuamua, arrived in October 2017. Its name, from Hawaiian, means scout or messenger, a fitting title for humanity's first identified visitor from another star. Oumuamua's discovery was serendipitous. It had already passed perihelion when astronomers at the Pan-STARRS telescope in Hawaii spotted it. Follow-up observations revealed a hyperbolic orbit, proof that it wasn't bound to the sun. It was just passing through. Oumuamua was strange from the start. It was elongated perhaps 10 times longer than it was wide, like a cigar or a shard of ice. It tumbled chaotically, its brightness fluctuating as it rotated. And as it receded from the sun, something unexpected happened. It accelerated. Not much, just a few millimeters per second squared, but enough to be measurable and significant. Researchers quickly identified this as non-gravitational acceleration. The most likely explanation was outgassing, just like a comet. But there was a problem. No coma, no tail, no visible signs of cometary activity. Sensitive observations found no trace of water vapor, carbon monoxide, or any of the usual suspects. Yet the acceleration was there. One hypothesis, proposed by researchers including Abraham Loeb at Harvard University, suggested that Oumuamua might be extremely lightweight, perhaps a thin reflective sheet propelled by solar radiation pressure, like a sail. Another idea was that it outgassed hydrogen, a molecule so light and transparent it would be nearly impossible to detect. Both explanations were controversial, sparking debates that continue today. Then came 2I Borisov in August 2019. Unlike Oumuamua, Borisov was unambiguously a comet. It had a prominent coma, a dust tail, and spectroscopy revealed familiar molecules: water, carbon monoxide, cyanogen. Its composition was remarkably similar to solar system comets, suggesting that comet formation might be a universal process. And crucially, Borisov showed measurable non-gravitational acceleration, about 3.8 x 10 to 7 meters per second squared, consistent with the observed outgassing. Borisov played by the rules. It was a comet, it looked like a comet, and it behaved like a comet. Astronomers breathed a sigh of relief. The universe made sense again. Now enter 3I Atlas. On the surface, it resembles Borisov more than Oumuamua. It has a coma. It shows spectroscopic evidence of gas release. It's visibly active. But its orbit is purely gravitational. No. Measurable NGA. It's as if someone took Borisov's appearance and Oumuamua's behavior, then mixed them in a way that shouldn't be possible. Let's put this in perspective. When a comet releases gas, the effect on its orbit depends on several factors: the rate of outgassing, the mass of the comet, the direction of the jets, and how long the outgassing lasts. For a typical comet, even modest outgassing, a few tons of material per second, can produce a detectable NGA over weeks or months. 3I Atlas is estimated to have a mass of roughly 3.3 x 1010 metric tons, based on its brightness and assumed size. That's a substantial mass comparable to a small mountain, but even a massive comet should show some recoil if it's losing material. To produce zero measurable NGA, one of the following must be true. The outgassing is perfectly symmetric in all directions, so the momentum vectors cancel out completely. The outgassing is so weak that its effect is below detection limits, even though the coma is visible. The object's mass is far greater than estimates suggest, making the recoil negligible. Something else is happening, something we don't yet understand. Let's consider each possibility. Perfect symmetry is unlikely. Comet nuclei are irregular. They have craters, ridges, cliffs, and vents. As they rotate, different areas face the sun at different times, creating asymmetric heating and outgassing. Even if jets erupted from multiple locations, achieving exact balance would require a level of coordination that nature doesn't typically provide. It's like expecting a dozen garden hoses, spraying in random directions, to perfectly cancel out their recoil. Possible? In theory. Plausible? Not really. Weak outgassing doesn't fit either. The coma is visible. Hubble and JWST have confirmed it. Spectroscopy shows molecular emission lines. The outgassing isn't negligible. It's producing a cloud tens of thousands of kilometers across. If the outgassing were too weak to affect the orbit, the coma shouldn't be this prominent. Could the mass be underestimated? That's more interesting. Mass estimates for distant objects rely on assumptions about reflectivity, albedo, size, and composition. If 3I Atlas has an unusually low albedo, meaning it reflects very little light, it could be larger and more massive than current estimates. A more massive object would require stronger outgassing to produce the same NGA. But even accounting for a factor of 2 or 3 in mass uncertainty, the lack of NGA is still puzzling, which leaves us with option 4, something we don't understand. This tension between visible activity and absent dynamics is unprecedented. Oumuamua had dynamics without visible activity. Borisov had both. 3I Atlas has activity without dynamics. It's the inverse of Oumuamua's riddle, but no less confounding. What makes this even more striking is the composition. Early spectroscopy detected cyanogen, Cn, and diatomic carbon, C2, molecules commonly found in comets. But there was also something unusual: emission lines consistent with nickel, but no corresponding iron. In solar system comets, metals like iron and nickel are usually found together, locked inside mineral grains. Seeing nickel without iron is like finding salt without pepper, technically possible, but odd. The James Webb Space Telescope's infrared observations added another layer. The thermal signature suggested a surface temperature consistent with solar heating, but no obvious hotspots or localized jets. The heat distribution appeared relatively uniform, as if the object were passively warming in the sun's light, rather than erupting with localized outgassing. All of this paints a picture of an object that doesn't quite fit any existing category. It's not a passive asteroid, there's too much evidence of activity. It's not a typical comet, the orbit is too clean. It's something in between, or perhaps something entirely new. And it's getting closer. By mid-June 2025, 3I Atlas had crossed the orbit of Jupiter. It was now less than 4 astronomical units from the Sun, approaching at nearly 30 kilometers per second. The countdown to perihelion continued. Observatories around the world kept their instruments trained on the visitor, recording every flicker, every spectral line, every tiny wobble in its position. Because the truth is, we don't get many chances like this. Interstellar objects are rare. Detecting them is hard. Studying them before they disappear back into the void is even harder. 3I Atlas is only the 3rd confirmed interstellar object in human history, and it's presenting us with a puzzle we've never seen before. What if this is our only opportunity to understand something fundamental about the universe? What if the answer to this riddle changes how we think about comets, about interstellar space, or about the possibilities of what can exist out there? The facts are extraordinary enough, but the implications are just beginning to unfold. To understand why the absence of non-gravitational acceleration is so troubling, we need to dive into the physics of outgassing itself. This isn't abstract theory, it's a process astronomers have observed and measured for decades, and every single time, without exception, active comets show the expected recoil. Until now. When a comet approaches the Sun, solar radiation heats its surface. Comets are made mostly of ice, not just water ice, but also frozen carbon monoxide, carbon dioxide, methane, and ammonia. These substances are called volatiles because they sublimate easily, transitioning directly from solid to gas when warmed. As the ice heats up, molecules break free from the surface and escape into space. This escaping gas doesn't just drift away gently, it erupts in jets, sometimes at speeds of hundreds of meters per second. Imagine a punctured tire releasing air. The gas rushes out with force. That force has to come from somewhere, and by Newton's third law, the comet recoils in the opposite direction. This is non-gravitational acceleration. The magnitude of the acceleration depends on several factors. First, the outgassing rate, how much mass is being ejected per second. Second, the velocity of the escaping gas. Third, the direction of the jets relative to the comet's motion. And fourth, the mass of the comet itself. More massive comets require stronger outgassing to produce the same acceleration. Let's use a metaphor. Imagine you're holding a garden hose that's spraying water. The water comes out fast, and you have to lean back to keep your balance. That backward push is the recoil. Now imagine trying to push a loaded cargo ship with the same garden hose. The ship won't budge, it's too massive. But here's the key. Even though the ship doesn't move noticeably, the force is still there. If you had sensitive enough instruments, you could measure it. With comets, our instruments are sensitive enough. Orbital tracking can detect accelerations as small as a few millionths of Earth's gravity. That's why astronomers routinely measure non-gravitational forces on comets, even when those forces are tiny. For comparison, consider comet Hale-Bopp, one of the most studied comets in history. During its 1997 apparition, Hale-Bopp exhibited a non-gravitational acceleration of roughly 5 × 10⁶ meters per second squared. That's about 1/1,000,000% of Earth's gravity, minuscule by everyday standards, but easily measurable over weeks and months of observation. The acceleration was consistent with the comet's observed outgassing rate, which peaked at about 300 tons of water vapor per second near perihelion. 2I Borisov, the second interstellar object, had a much smaller NGA, 3.8 × 10⁷ meters per second squared. That's about 10 times weaker than Hale-Bopp, but still well within detectable limits. Borisov's outgassing was less vigorous, understandable for a comet on its first pass through the inner solar system, still pristine and cold, even faint, distant. Comets show measurable NGA. Comet 67P Churyumov-Gerasimenko, the target of the European Space Agency's Rosetta mission, had an NGA of about 2 × 10⁷ meters per second squared during its 2015 perihelion passage. Rosetta observed jets erupting from the comet's surface, measured the gas flow, and confirmed that the observed acceleration matched predictions. The point is this: whenever astronomers see a comet with a visible coma and spectroscopic evidence of outgassing, they also measure non-gravitational acceleration. The two always go together. It's not a coincidence, it's cause and effect, except with 3I Atlas. The orbit has been tracked for months now, with data from multiple observatories. The Minor Planet Center has collected thousands of position measurements. When orbital dynamicists fit those measurements to a trajectory, they use models that include both gravitational forces, the Sun, planets, and non-gravitational forces, outgassing. The gravitational model fits perfectly. Adding NGA terms doesn't improve the fit, in fact, it makes it worse. The data strongly suggest that any NGA, if present, is below detection limits. Current detection limits for NGA are around 1 × 10⁸ meters per second squared, given enough observations over time. That's about 100 times weaker than Borisov's NGA. For 3I Atlas to have an NGA below this threshold, while still producing a visible coma, the outgassing would need to be either incredibly weak or incredibly symmetric. Let's explore the symmetry angle more carefully. Suppose 3I Atlas has jets erupting from all over its surface, pointing in every direction. If these jets were perfectly balanced, equal force north, south, east, west, the net momentum would be zero, and there'd be no NGA. But achieving this requires extreme precision. Real comet nuclei aren't smooth spheres. They're lumpy, cratered, and irregular, more like potatoes than billiard balls. The surface composition varies from place to place. Some areas are icy, others are covered in dark refractory dust. As the comet rotates, different regions face the sun, heating unevenly. This creates localized jets, not uniform outgassing. Consider Comet Hartley 2, visited by NASA's Deep Impact spacecraft in 2010. Hartley 2 had distinct jet sources, specific vents on the surface, where gas and dust erupted. The jets weren't evenly distributed. They came from the comet's waist and ends, driven by pockets of frozen carbon dioxide. The result was a measurable asymmetric NGA. Or look at Comet 67P, studied in exquisite detail by Rosetta. Its jets were highly localized, often emanating from cliffs and pits. The outgassing varied with the comet's rotation, creating a complex pattern of activity, again asymmetric, again producing measurable NGA. For 3I Atlas to have symmetric outgassing, its surface would need to be remarkably uniform. Either that, or it would need to have so many jets, pointing in so many directions, that they averaged out to zero. Both scenarios are possible in principle, but neither is common in nature. There's another possibility. Maybe the outgassing isn't continuous. Maybe it's pulsed brief bursts, separated by long, quiet periods. If the bursts occurred randomly in different directions, they might cancel out over time, producing no net NGA. But this doesn't match what we see. The coma is persistent, not flickering on and off. Hubble images taken weeks apart show a steady glow, suggesting continuous activity. So we're left with a paradox. The coma is real, the spectroscopy is real, the outgassing is happening, but the orbit is clean. No measurable non-gravitational acceleration. What are we missing? One speculative idea is that the object might have an internal structure that dampens or redirects the momentum of outgassing. Imagine a sponge-like interior with interconnected pores and channels. Gas generated deep inside could migrate through the interior, escaping from multiple locations in a way that naturally balances the momentum. It's a stretch, but not impossible. Another idea involves the role of dust. When gas escapes from a comet, it often carries dust grains along. These grains can absorb momentum, effectively spreading out the recoil force. If 3I Atlas produces a lot of dust, much more than typical comets, the dust cloud might act as a buffer, preventing the nucleus from recoiling noticeably. But again, observations don't support this. The coma appears gas-dominated, with no obvious excess of dust. We could also consider the object's rotation. If 3I Atlas rotates very slowly, different parts of the surface would face the sun for extended periods, potentially allowing for more symmetric heating. But even slow rotation doesn't guarantee symmetry. Comet 67P rotates every 12 hours, yet its outgassing is still asymmetric. The bottom line is that all conventional explanations require special conditions that, while not impossible, are statistically unlikely. It's like flipping a coin and getting heads 20 times in a row. Sure, it could happen, but you'd start to wonder if something else is going on. And that's where the unease comes from. Because if 3I Atlas isn't following the rules we've established through centuries of observation, then either it's a 1 in a million oddball, or our understanding of cometary physics is incomplete. The facts are extraordinary enough, but the uncertainty, that's what drives the investigation forward. Beyond the orbital dynamics, there's another layer to the mystery, the chemistry. The spectrum of 3I Atlas, the fingerprint of light it emits and absorbs, reveals a composition that's both familiar and strange. And like the missing non-gravitational acceleration, the chemical signature doesn't quite fit expectations. Spectroscopy is one of astronomy's most powerful tools. When molecules in a comet's coma are energized by sunlight, they emit light at specific wavelengths, creating a unique pattern of bright lines in the spectrum. By identifying these lines, astronomers can determine which molecules are present and in what quantities. It's like reading a chemical barcode. For 3I Atlas, early spectroscopy from the Gemini South Telescope in Chile and the Very Large Telescope, VLT, in the Atacama Desert, detected several familiar molecules. Cyanogen, CN, was prominent, producing strong emission at 388 nanometers. Diatomic carbon, C2, appeared at 516 nanometers. Weaker signals hinted at hydroxyl, OH, a fragment of water molecules broken apart by sunlight. So far, so normal. CN, C2, and OH are common in comets. They're the building blocks of the dusty, icy bodies we've been studying for generations. But then came something unexpected, emission lines consistent with neutral nickel atoms. Nickel in a comet's coma is unusual but not unheard of. In 2021, researchers analyzing archival spectra from dozens of comets discovered that many showed faint nickel and iron emission, likely from tiny metal grains. Vaporized near the sun, the metals were trace components locked inside silicate and sulfide minerals. When these grains sublimated or fragmented, they released atoms of iron and nickel into the coma. The key word there is "and." Iron and nickel almost always appear together. They're chemically similar, often found in the same minerals like olivine, pyroxene, and troilite. If you detect one, you expect to detect the other. But in 3I Atlas, the nickel lines were clear, while iron was absent or at E. Least far weaker than expected. It's like finding footprints in the sand, but only the left foot over and over. Something's off. Why would nickel appear without iron? There are a few possibilities. First, maybe the composition of the dust grains is unusual, rich in nickel-bearing minerals but poor in iron. Second, maybe the physical conditions in the coma favor nickel emission over iron. Or third, maybe the detection is a fluke, an artifact of noise or instrumental effects. Let's consider the first option. On Earth, nickel-rich minerals do exist. Pentlandite, for example, is an iron-nickel sulfide, but its nickel-to-iron ratio can vary. In meteorites, especially iron meteorites, nickel concentrations can be quite high, sometimes exceeding 10% by mass. But even in nickel-rich meteorites, iron is still present. Finding pure nickel without any iron is difficult to explain geologically. Could 3I Atlas have formed in an environment where iron was depleted, perhaps in a region of its parent? Protoplanetary disk, where chemical conditions favored nickel over iron. That's speculative, but not impossible. Protoplanetary disks are complex, with temperature and pressure gradients that can fractionate elements in unexpected ways. Still, such extreme fractionation enough to produce nickel without iron would be rare. The second option involves excitation and emission. Nickel atoms emit light when electrons jump between energy levels. The strength of these emissions depends on the atom's temperature and the intensity of ultraviolet radiation from the sun. Maybe in the conditions of 3I Atlas's coma, nickel emissions are easier to detect than iron's. But astronomers are familiar with both nickel and iron spectra in comets. If iron were present in comparable amounts, it should show up. The fact that it doesn't is puzzling. The third option, that it's a detection artifact, can't be ruled out entirely, but it seems unlikely. Multiple observations from different instruments have confirmed the nickel signal. The VLT, Gemini South, and even high-resolution spectra from the James Webb Space Telescope all show the same pattern. If it were noise, it wouldn't be consistent across platforms. So the chemistry is odd. Not impossible, but odd. And when you combine this oddity with the missing NGA, the picture becomes even murkier. There's also the question of volatiles, the gases themselves. The detection of CN and C2 suggests the presence of complex organic molecules, possibly long-chain hydrocarbons that break down under solar radiation. The weak OH signal implies some water, but not in large amounts. This is somewhat reminiscent of 2I Borisov, which also had carbon-rich chemistry, but there's a difference in degree. Borisov's water emission was stronger, more typical of solar system comets. 3I Atlas seems to be more carbon-heavy, less water-dominated. What does that mean? It could indicate that 3I Atlas formed farther from its host star than Borisov did, in a colder region where carbon monoxide and carbon dioxide ices were more abundant than water ice. Or it could mean that the object experienced significant heating at some point in its history, losing its water ice and retaining the more refractory carbon compounds. Either way, it suggests a different formation history. Here's another piece of the puzzle: the coma's color. Photometric observations measuring the brightness of the coma at different wavelengths show that it's slightly redder than typical. Solar system comets. The reddening isn't extreme, but it's noticeable. Red coloration in comets usually comes from organic compounds, complex carbon-based molecules that absorb blue light and reflect red. These organics are sometimes called tholins, a term coined by astronomer Carl Sagan to describe the reddish-brown gunk that forms when simple organic molecules are exposed to ultraviolet radiation over long periods. Tholins are common in the outer solar system. They coat the surfaces of Kuiper, belt objects, give Saturn's moon Titan its hazy atmosphere, and appear in comets that have spent eons in deep space. The presence of tholins in 3I Atlas's coma suggests that the object has been wandering through interstellar space for a very long time, long enough for cosmic rays and starlight to cook its surface ices into complex organics. But here's the interesting part. Tholins are fragile. When a comet enters the inner solar system and heats up, tholins tend to break down, releasing simpler molecules like CN and C2, exactly what we're seeing. So the red color and the spectroscopic detections are consistent. They tell a story of an ancient object processed by radiation, now awakening as it nears the sun. Yet even this narrative has a wrinkle. The James Webb Space Telescope's infrared observations, taken in July 2025, revealed something unexpected in the coma's thermal structure. The temperature distribution was more uniform than anticipated. Typically, when a comet outgasses, certain regions like the subsolar point, where the sun's rays strike most directly, become much hotter than others. This creates thermal gradients, hotspots that show up clearly in infrared images. 3I Atlas didn't show strong hotspots. The thermal signature was relatively even, as if the entire surface were warming gently and uniformly. This could mean several things. Maybe the surface is covered in a thick layer of insulating dust, which smooths out temperature variations. Maybe the object rotates so rapidly that no single spot stays in sunlight long enough to overheat. Or maybe the outgassing itself is so distributed, coming from so many small vents across the surface, that it cools the object evenly through sublimation. None of these explanations are perfect. A thick dust layer would likely suppress outgassing, yet we see a prominent coma. Rapid rotation could explain the thermal uniformity, but rotation rates can be measured by watching brightness variations as the object spins. So far, light curve observations haven't detected a clear rotation period, another oddity. It's as if the object either rotates very slowly, or its shape and albedo are so uniform that rotation doesn't cause noticeable brightness changes. Both scenarios are unusual. The distributed outgassing idea is intriguing, but requires a very specific surface structure essentially, a sponge-like or porous exterior with countless tiny vents. Such a structure isn't impossible. Some models of comet nuclei propose a rubble pile configuration, where the nucleus is a loose aggregate of smaller chunks held together by weak gravity. If 3I Atlas were a rubble pile, gas could percolate through the gaps between chunks, escaping from many locations simultaneously. This might explain both the uniform thermal signature and the lack of measurable NGA, if the outgassing truly is omnidirectional. But again, this is speculation. We don't have direct images of the nucleus. We can't see its shape or surface features. All we have is the coma, the cloud of gas and dust that shrouds the nucleus like a veil. The coma tells us something is happening, but it hides the details. Another chemical clue comes from isotope ratios. Isotopes are variants of the same element with different numbers of neutrons. For example, deuterium is a heavy isotope of hydrogen. The ratio of deuterium to regular hydrogen in water, expressed as DH, can reveal where the water formed. Deuterium-rich water typically comes from cold environments, where heavy isotopes are preferentially incorporated into ice. In solar system comets, DH ratios vary, but they generally fall within a certain range. Oort cloud comets tend to have higher DH ratios, while Jupiter family comets have lower ones. 2I Borisov's DH ratio, measured from its water emission, was within the range of solar system comets, another sign that comet formation is a universal process. Attempts to measure 3I Atlas's DH ratio have been hampered by the faintness of the water signal. The OH emission is weak, making it difficult to extract precise isotope measurements. But preliminary analyses suggest the ratio might be slightly higher than typical, implying formation in a very cold environment, perhaps in the outskirts of another star system. This would be consistent with the object's carbon-rich chemistry and long interstellar journey. Still, uncertainties are large. Confirming the DH ratio will require more sensitive observations, possibly from the Atacama Large Millimeter Array, ALMA in Chile, which can detect molecular line emission with exquisite precision. If ALMA time is allocated before 3I Atlas fades from view, we might get a clearer answer. For now, the chemistry paints a picture of an object that's both familiar and alien. Familiar in its basic ingredients: carbon, nitrogen, oxygen, metals, but alien in the details. The nickel without iron, the carbon-heavy coma with weak water, the uniform thermal signature. Each piece is a clue, but the overall picture remains frustratingly incomplete. And beneath all this lies the central enigma, the missing non-gravitational acceleration. Because no matter how unusual the chemistry is, it doesn't change the fundamental physics. If gas is escaping, momentum must be conserved. The object must recoil, yet it doesn't. What are we not seeing? What mechanism could suppress or hide the expected acceleration? The chemistry might offer a hint, but it doesn't provide an answer. Not yet. As 3I Atlas continues its approach, The chemical investigations intensify. More spectra, more photometry, more infrared observations. Each data set adds a brushstroke to the portrait, revealing a visitor unlike any we've encountered before. But time is running short. Perihelion is approaching, and with it the best chance we'll ever have to solve this mystery. If the chemistry is puzzling and the missing acceleration is baffling, then the question of mass becomes critical, because in the end, the magnitude of non-gravitational acceleration depends not just on outgassing strength, but on the object's mass. A more massive object requires stronger outgassing to produce the same NGA. So if we've underestimated 3I Atlas's mass, if it's far heavier than we think, that could explain why the acceleration is undetectable. But here's the problem. Making the object massive enough to hide the NGA requires assumptions that strain credibility. Let's start with the basics. An object's mass is notoriously difficult to measure from Earth unless it has a moon or affects other bodies gravitationally. For solitary asteroids and comets, astronomers estimate mass indirectly, using brightness, size, and assumed composition. The logic goes like this. Measure the object's brightness, apparent magnitude, estimate how reflective it is, albedo, calculate its size, then multiply by an assumed density to get mass. Each step involves assumptions. For 3I Atlas, the apparent magnitude in late July 2025 was around 19.5 faint, but within reach of professional telescopes. To convert this to size, you need to know the albedo. Comet nuclei typically have low albedos, around 4% to 6%, because they're covered in dark carbon-rich material. Assuming an albedo of 5%, the nucleus would be roughly 4 to 5 kilometers in diameter. Now apply a density. Comet nuclei are fluffy, porous objects with densities around 400 to 600 kilograms per cubic meter, less dense than ice, more like compacted snow. Using a density of 500 km3 and a diameter of 4.5 kilometers, the estimated mass is about 3.3 x 1010 metric tons. That's the baseline estimate, a substantial mountain of ice and rock tumbling through space. But what if the albedo is wrong? What if 3I Atlas reflects even less light than typical comets, say, an albedo of 2%? Lower albedo means the object must be larger to produce the same brightness. With a 2% albedo, the diameter jumps to about 7 kilometers. If the density stays at 500 kilojoules m3, the mass becomes roughly 1.5 x 10 to the 11 metric tons, about 5 times heavier. That's still not enough. Here's why. The coma is visible. Gas is escaping. Even with conservative estimates, the outgassing rate is likely around 10 to 100 kilograms per second, modest by cometary standards. If that gas exits at a typical velocity of 500 meters per second, reasonable for sublimating water or carbon monoxide, it exerts a force on the nucleus. Newton's second law tells us that force equals mass times acceleration, F as ma. Rearranging, acceleration equals force divided by mass, a French Fm. The force from outgassing is the mass loss rate times the gas velocity. For an outgassing rate of 50 kilojoules s and a velocity of 500 millimeters per s, the force is 25,000 newtons. Divide that by the baseline mass of 3.3 x 1010 metric tons, 3.3 x 1013 kilograms, and you get an acceleration of about 7.6 x 10 to 10 meters per second squared. That's tiny, almost 100 times smaller than detection limits. So maybe the outgassing is just too weak to measure. But here's the catch. If the outgassing is that weak, the coma should be fainter. A coma's brightness depends on how much gas and dust is present. Observations suggest the coma is moderately bright, implying an outgassing rate toward the higher end of the range, closer to 100 kds or more. At 100 kgs and 500 ms, the force doubles to 50,000 newtons, and the acceleration becomes 1.5 x 10 9 mm s2. Still small, but getting closer to detectable. Now let's push the mass higher. Suppose the E albedo is incredibly low 1%, and the density is higher than expected, say 1000 kilo m3, solid ice instead of fluffy snow. The diameter would be around 10 kilometers, and the mass would be roughly 5x 10 to 11 metric tons. At that mass, even an outgassing rate of 100 kDa/s produces an acceleration of only 1 × 10⁹ m/s², still borderline detectable, but within the noise. But there's a problem. Objects with such low albedos and high densities are rare. Asteroids can be dense metallic asteroids. For instance, have densities around 7,000 km3. But metallic asteroids don't outgas. They don't have comae. The very fact that 3I Atlas is active suggests it contains volatiles ices which inherently lower the density. You can't have it both ways. You can't have a dense metallic-like object that also behaves like a comet. The physics doesn't allow it. Think of it this way. Imagine you're trying to push a shopping cart full of groceries. If the cart is light, a gentle push gets it moving. If the cart is heavy loaded with bricks instead of bread, you need to push much harder to achieve the same acceleration. Now imagine the cart is so heavy that even a strong push barely moves it. That's what we'd need with 3I Atlas, an object so massive that the push from outgassing is negligible. But here's the kicker. That massive object is still losing material, it's still leaking gas. And eventually you run into a conservation problem. The outgassing has to come from somewhere. If the object is truly gigantic, tens of kilometers across, trillions of tons in mass, it can sustain outgassing for a long time. But it also becomes harder to explain how such a massive, icy body could survive the journey through interstellar space without being torn apart by tidal forces, collisions, or internal heating. There's another angle to consider: asymmetry. Even if the object is massive, asymmetric outgassing should still produce Torque's rotational accelerations. When jets fire from off-center locations, on a comet, they don't just push the comet linearly, they also spin it. This spin up or spin down should be detectable in light curves as changes in rotation period. So far, no clear rotation signal has been detected for 3I Atlas. Light curves show some variation, but it's erratic, not periodic. That's unusual. Most comets have measurable rotation periods, typically ranging from a few hours to a few days. The absence of a clear period suggests either that the object rotates very slowly once every many days or weeks, or that its shape and surface are remarkably uniform, so rotation doesn't cause brightness changes. Both scenarios are unlikely. Slow rotation would mean the object spins less than once every several days, which is unusual for objects this size. And perfect uniformity in shape, albedo, and surface features is almost unheard of in nature. Unless, of course, the object isn't natural. That's a thought that lingers at the edge of the conversation, unspoken but unavoidable. If natural processes can't easily explain the observations, then what? The scientific method demands that we exhaust all natural explanations before considering alternatives. But the mass argument is closing that door. To hide the NGA through mass alone requires assumptions that are progressively harder to justify. Could 3I Atlas be hollow, a shell of ice surrounding an empty core? That would increase its size without increasing its mass proportionally, lowering the average density. But hollow. Structures are unstable. Gravitational forces and internal stresses would tend to collapse them over time, and even if a hollow structure somehow survived, the outgassing would still occur from the outer shell, producing asymmetries. Could the object be a binary two bodies orbiting each other closely, appearing as a single object from Earth? Binary comets exist, though they're rare. If 3I Atlas were a binary, the combined mass might be higher than estimates based on a single nucleus. But binary systems usually reveal themselves through light curve variations as the two bodies eclipse or reflect light differently. No such variations have been convincingly detected. The mass argument leads to a frustrating conclusion. No reasonable combination of mass, albedo, and density fully explains the missing NGA without invoking special circumstances. You can make it work, but only by stacking assumptions: low albedo, high density, perfectly symmetric outgassing, slow or absent rotation. Each assumption individually is plausible. Together they strain coincidence, and that's the heart of the mystery. 3I Atlas isn't impossible, it's improbable. It's the kind of object that, if you encountered it once, You might shrug and call it an outlier. But when you examine it closely, when you try to fit all the pieces together, the picture doesn't quite resolve. So what are we looking at? A cosmic oddball? A one-in-a-billion statistical fluke? Or something else entirely? The facts are extraordinary enough. But the mass argument forces us to confront the limits of our explanations. And as 3I Atlas closes in on perihelion, those limits are becoming harder to ignore. By August 2025, the Hubble Space Telescope had been observing 3I Atlas for nearly 4 months. Hubble's ultraviolet and visible light cameras, though aging, remain some of the best tools for studying faint, distant objects. And what Hubble was seeing only deepened the mystery. Hubble's advanced camera for surveys, ACS, captured images of the coma at multiple wavelengths. The coma extended roughly 40,000 kilometers from the nucleus, about 3 times the diameter of Earth. It glowed faintly, backlit by the sun, a diffuse cloud of gas and dust particles scattering sunlight in all directions. In ultraviolet light, the coma was brighter, a sign that hydroxyl radicals, OH, were abundant fragments of water molecules split apart by solar radiation. But there was something odd about the coma's morphology. Most comets show a distinct asymmetry in their comae. The side facing the sun is brighter and more active, while the trailing side fades. This is because solar heating drives outgassing, and the illuminated hemisphere receives more energy. Additionally, as the comet moves through space, the gas and dust get swept back by solar wind and radiation pressure, creating the characteristic tail. 3I Atlas's coma was more symmetric than expected. The brightness distribution was nearly spherical, with only a slight elongation in the anti-sunward direction. There was a tail faint but present, but it was shorter and less pronounced than what you'd see in a comet of comparable activity. It was as if the outgassing was so evenly distributed around the nucleus that no single side dominated. This observation aligned with the thermal data from JWST. If the surface temperature was relatively uniform, then outgassing might also be uniform, producing a symmetric coma. But again, achieving this naturally is difficult. Hubble also monitored the coma's variability over time. Some comets undergo outbursts, sudden increases in brightness, caused by abrupt releases of gas and dust. These outbursts can last hours or days, dramatically brightening the coma before fading back to normal. Outbursts are thought to result from the exposure of fresh ice, the collapse of surface layers, or the eruption of subsurface volatile pockets. 3I Atlas showed no outbursts. Its brightness varied slightly from day to day, but these variations were gradual and seemed to correlate with the object's changing distance from the sun. As it drew closer, it brightened steadily, as expected. But there were no spikes, no sudden flares. The activity was remarkably stable. Stability in a comet can be either reassuring or unsettling. On one hand, it suggests a mature, well-regulated outgassing process, perhaps driven by deep-seated ice layers that sublimate at a constant rate. On the other hand, it's unusual. Comets are chaotic. Their surfaces crack, peel, and shed dust. They spin unevenly. They outburst. Seeing such stable behavior is like watching a perfectly calm lake pleasant, but you start to wonder why there are no ripples. Hubble also attempted to detect the nucleus directly, the solid body at the heart of the coma. This is challenging because the coma's glow overwhelms the faint reflected sunlight from the nucleus. But by carefully subtracting a model of the coma's brightness, astronomers can sometimes reveal the nucleus underneath. For 3I Atlas, the nucleus remained elusive. Either it was too small, too dark, or too deeply embedded in the coma to resolve. The best estimates, based on the overall brightness and assumed albedo, place the nucleus diameter at around 4 to 5 kilometers, roughly the size of a small mountain. But without a direct detection, uncertainty remained. One intriguing observation came from polarimetry, measuring the polarization of light reflected by the coma. Polarization occurs when light waves align in a particular direction, and it can reveal information about the size, shape, and composition of dust particles in the coma. Hubble's polarimetric observations, conducted in mid-August, showed that the light from 3I Atlas's coma was moderately polarized, consistent with dust grains in the size range of a few micrometers, typical for cometary dust. But the degree of polarization was slightly lower than expected, suggesting either fewer dust grains or grains with unusual optical properties. Lower dust content would align with the gas-dominated coma seen in spectroscopy. It would also mean that the outgassing is relatively clean, releasing gas without entraining much dust. This happens when the nucleus is covered in a thin layer of volatile ice, which sublimates without dragging along heavy dust particles. Alternatively, the dust grains might be fluffier or more porous than typical, scattering light differently and reducing polarization. Either way, the polarimetry added another piece to the puzzle. 3I Atlas's coma is unusual, not just in its symmetry and stability, but also in its dust-to-gas ratio. Hubble's observations were shared widely among the astronomical community. Papers were drafted, preliminary results circulated. The consensus was cautious. 3I Atlas is clearly active, clearly anomalous, and clearly worth continued observation. But no one was ready to make bold claims. Not yet. Because the truth is, anomalies come in two flavors. Some are harbingers of discovery, the first hints of something new and important. Others are red herrings, quirks of measurement, misunderstandings, or rare but ultimately mundane configurations. Distinguishing between the two requires time, data, and patience. 3I Atlas was being given all three, and as the object moved past the orbit of Mars in late August, the pace of observations accelerated. More telescope time was allocated, more proposals submitted. The countdown to perihelion continued, and, with it, the pressure to find answers. But Hubble could only do so much. It had given us high-resolution images, ultraviolet spectra, and polarimetry. It had shown us a coma that defied easy categorization: symmetric, stable, gas-rich, and persistently active. What Hubble couldn't tell us was why. For that, we'd need other eyes, other instruments, other perspectives. And so the investigation broadened, pulling in observatories across the globe and beyond. The mystery of 3I Atlas was no longer a quiet curiosity. It was becoming a global scientific campaign. If Hubble provided the visible and ultraviolet view, the James Webb Space Telescope offered something else entirely: the infrared perspective. JWST, launched in late 2021 and operational since mid-2022, is the most powerful infrared observatory ever built. It can peer through dust clouds, detect faint heat signatures, and resolve details invisible to optical telescopes. For studying 3I Atlas, JWST was essential. In early September 2025, JWST's near-infrared camera, NEIR-CAM, captured a series of images of the approaching object. The observations were conducted at multiple wavelengths, from 1 to 5 micrometers, covering a range sensitive to thermal emission and reflected sunlight. The goal was to map the temperature distribution of the coma and, if possible, detect the nucleus. What JWST found was both illuminating and perplexing. The infrared images showed a warm coma, glowing at wavelengths consistent with temperatures around 200 to 250 Kelvin, about -23 to -73 degrees Celsius. This is warmer than you might expect for an object at 2.5 astronomical units from the Sun, where 3I Atlas was located in early September. For comparison, the equilibrium temperature of a passive, non-rotating body at that distance would be around 180 Kelvin. The extra warmth suggested active heating energy being absorbed and re-radiated, likely driven by outgassing. But again, the temperature distribution was strikingly uniform. No obvious hotspots, no localized regions of intense activity, just a smooth, diffuse glow. JWST's mid-infrared instrument, MIRI, operating at longer wavelengths, 5 to 28 micrometers, provided additional data. MIRI is sensitive to cooler thermal emission and can detect dust grains and ice particles. The MIRI spectra showed absorption features consistent with water ice and carbonaceous material, again, typical for comets. But the features were broader and less sharply defined than usual, suggesting either complex mixtures or unusual grain structures. One particularly interesting detail emerged from the 10-micrometer silicate feature, a broad absorption band caused by silicate minerals in dust grains. In solar system comets, this feature is prominent, indicating the presence of rocky material mixed with ice. In 3I Atlas, the silicate feature was present but weaker, suggesting less silicate dust or smaller grain sizes. This aligns with Hubble's polarimetry results. Less dust, or dust with unusual properties. Together, the observations paint a picture of an object dominated by volatiles gas and simple ices with relatively little rocky material. JWST also attempted spectroscopy in the near-infrared targeting molecular absorption bands. Carbon monoxide, CO, has a strong absorption feature near 4.67 micrometers, and JWST is capable of detecting it even at low concentrations. The observations, conducted over several nights in mid-September, revealed a faint but definite CO signal. Carbon monoxide is a key molecule in comets. It's one of the most volatile ices, sublimating at temperatures as low as 25 Kelvin. In the outer solar system, beyond Neptune, CO ice is stable. Closer to the Sun, it sublimates, driving outgassing even at large distances. The detection of CO in 3I Atlas confirmed that the object contains highly volatile ices, consistent with formation in a cold environment. But here's the twist. The amount of CO detected was less than expected, given the object's brightness and distance. In 2I Borisov, CO was abundant, accounting for a significant fraction of the outgassing. In 3I Atlas, CO was present, but subdued. This might indicate that the object is relatively depleted in CO, or that the CO is buried beneath layers of less volatile material like water ice. Depletion is interesting because it suggests processing. If 3I Atlas had experienced heating in the past, perhaps during a close encounter with a star, or through internal radioactive decay, it might have lost much of its CO, leaving behind the less volatile ices. This would make it an older, more evolved object. Alternatively, the CO could be concentrated in certain regions of the nucleus, outgassing only when those regions face the Sun. If the rotation is slow, some areas might remain in shadow for long periods, preventing CO sublimation. But this brings us back to the rotation problem. Why is there no clear rotation signal? JWST's observations also provided constraints on the nucleus size. By measuring the total thermal emission and modeling the heat balance, astronomers estimated that the nucleus radiates roughly 2x 109 watts of thermal energy, equivalent to about 2,000 megawatts, or the output of 2 large power plants. This power comes from absorbed solar energy being re-emitted as infrared light. Using this thermal power and the observed temperature, you can estimate the emitting surface area, which in turn constrains the size. The calculations suggested a nucleus diameter in the range of 4 to 6 kilometers, consistent with earlier estimates based on brightness and albedo. But uncertainties remained large, especially regarding the albedo and the fraction of the surface that's actively outgassing. One of JWST's most valuable contributions was temporal monitoring. Over a 2-week period in September, JWST observed 3I Atlas multiple times, watching for changes in the coma's brightness, temperature, and spectral features. This kind of time series data can reveal outbursts, rotational variability, or long-term trends. What JWST saw was stability. Day after day, the coma looked the same. The temperature stayed within a narrow range. The CO signal remained steady. The brightness increased gradually, tracking the decreasing distance from the Sun, but there were no sudden changes. Stability, again. That word keeps appearing. In a way, the lack of variability is itself a result. It tells us that whatever process is driving the outgassing is remarkably consistent. There are no major disruptions, no sudden exposures of fresh ice, no catastrophic fractures. The object is behaving like a well-oiled machine, sublimating ices at a steady, predictable rate. But machines require regularity. They require structure. Natural comet nuclei, with their chaotic surfaces and irregular shapes, don't usually behave like machines. They're messy. They're unpredictable. So why is 3I Atlas so orderly? JWST couldn't answer that question directly, but it provided crucial data that narrowed the possibilities. The uniform temperature, the subdued CO, the stable outgassing all pointed toward an object with a remarkably homogeneous surface or a highly distributed outgassing mechanism. And beneath all this data, the central enigma persisted, the missing non-gravitational acceleration. Because no matter how uniform the outgassing, momentum still has to go somewhere. Newton's laws don't care about symmetry, they care about vectors. If gas is leaving the object must recoil, unless every vector cancels perfectly, which remains implausible. As September turned into October and 3I Atlas crossed inside the orbit of Mars, the JWST observations continued. Every spectrum, every image, every temperature map added to the growing archive, and with each addition, the picture became clearer and more mysterious. The facts are extraordinary enough, but the consistency, the orderliness, the refusal to behave like a normal comet, that's what gnaws at the edges of understanding. By early October 2025, one question loomed larger than most. Why can't we detect 3I Atlas's rotation? Every solid object in space rotates. Asteroids, comets, moons, they all spin, legacies of collisions, gravitational interactions, and the chaotic processes that form them. Rotation is fundamental, and for astronomers, measuring rotation is crucial because it reveals an object's shape, surface properties, and internal structure. Yet 3I Atlas resisted. Light curve observations' measurements of brightness over time should reveal rotation. As a non-spherical object spins, different sides come into view, reflecting varying amounts of sunlight. If one side is brighter, perhaps covered in more reflective ice, and the other is darker, covered in dust, the overall brightness oscillates with the rotation period. Most comets have light curve amplitudes of 0.1 to 0.5 magnitudes, meaning their brightness varies by 10% to 50% as they rotate. For 3I Atlas, the light curve was nearly flat. Multiple observatories tracked the object's brightness throughout August and September. The data showed small fluctuations, 0.05 to 0.1 magnitudes, but no clear periodicity. Some nights it was slightly brighter, other nights slightly dimmer, but the changes seemed random, not cyclical. Several explanations were proposed. First, the object rotates very slowly. If the rotation period is longer than the observing window, say, several days or even weeks, then light curve variations would be hard to detect. You'd see only a portion of the rotation cycle, not enough to identify the period. Slow rotation isn't unheard of. Some asteroids rotate once every few days. But for an object this small, a few kilometers across, slow rotation is unusual. Smaller objects tend to rotate faster, spun up by collisions or tidal interactions. Second, the object is nearly spherical, with a uniform surface. If 3I Atlas is round and covered in material of consistent reflectivity, rotation wouldn't cause brightness changes. But perfect spheres are rare in nature. Comets especially are irregular, shaped by outgassing, fractures, and collisions. Achieving a sphere requires either a large mass, so gravity smooths the shape, or very specific formation conditions. A 4-kilometer object shouldn't be spherical. Third, the rotation axis points toward Earth. Imagine watching a spinning top from directly above. You see it spin, but its brightness doesn't change because you're always looking at the same face. If 3I Atlas's rotation axis happened to align with our line of sight, we'd see minimal variation. This is geometrically possible, but it's a coincidence, and coincidences pile up. Fourth, the object is in a complex rotation state, tumbling chaotically, rather than spinning smoothly around a single axis. Chaotic rotation can produce erratic light curves without clear periodicity. This happens when an object's shape is highly irregular and its rotation is unstable. Oumuamua, for instance, showed evidence of chaotic tumbling, but chaotic rotation usually still produces variations, just not periodic ones. 3I Atlas's light curve is too stable for chaos. Fifth, the coma dominates. The coma's glow, being roughly symmetric, might overwhelm the faint reflected light from the nucleus. If the nucleus is small and dark, its rotation would cause only tiny brightness changes, easily drowned out by the steady glow of the coma. This is plausible, but even gas-rich comets sometimes show rotation signals when observed carefully. None of these explanations are satisfying on their own, but taken together, they suggest that something about 3I Atlas's physical state is preventing us from seeing its rotation. Either the rotation is genuinely slow, or the object's shape and surface are remarkably uniform, or the geometry is unfavorable, or some combination of all three. There's another method for detecting rotation: spectroscopy. If outgassing jets are localized on the nucleus, they'll fire as those regions rotate into sunlight. This can cause Doppler shifts in spectral lines, tiny changes in wavelength caused by motion toward or away from us. By monitoring spectral lines over time, astronomers can sometimes detect rotation periods even when light curves fail. In mid-September, the VLT conducted high-resolution spectroscopy of 3I Atlas, targeting the CN emission line at 388 nanometers. The observations spanned several hours, covering what should have been a significant fraction of a rotation cycle if the period were typical: a few hours. The CN line showed no measurable Doppler shifts. It remained stationary, centered at the rest wavelength, with no evidence of rotation-induced velocity changes. This could mean the jets are symmetric, firing in all directions equally, or that the rotation is indeed very slow, or that the jet's velocities are too small to produce detectable Doppler shifts. Once again, the observations pointed toward uniformity, symmetry, and stability traits that are individually possible but collectively improbable. And here's where the unease creeps in. Because if 3I Atlas truly has no measurable rotation, or rotates so slowly that it's effectively stationary, that raises deeper questions. How did it end up in such a state? Natural processes tend to impart spin. Collisions, tidal forces, asymmetric outgassing, they all add angular momentum. For an object to have little or no rotation, it would need to have lost that angular momentum somehow, or never acquired it in the first place. Losing angular momentum is possible through mechanisms like tidal braking if the object once orbited close to a planet or star, or internal friction if the interior is viscous and dissipates rotational energy. But 3I Atlas is an interstellar object, wandering freely through space for eons. There's no nearby star or planet to break its rotation tidally, and internal friction would take millions of years to slow rotation significantly possible, but it would require a very specific internal structure. Not acquiring angular momentum in the first place is even stranger. Objects form from collapsing clouds of gas and dust, which almost always carry some net angular momentum. Even tiny imbalances in the initial conditions lead to rotation. To form a non-rotating object would require extraordinary symmetry in the collapse symmetry that nature rarely provides. There's one more possibility, rarely discussed but worth considering. Perhaps 3I Atlas's rotation was deliberately stabilized. This is where speculation enters dangerous territory. Stabilizing rotation requires active control, torques applied at just the right moments to dampen rotational motion. In human spacecraft, this is done with reaction wheels, thrusters, or magnetic torquers. But in a natural comet, there's no known mechanism, unless, of course, the object isn't entirely natural. That thought hovers at the edge of scientific discourse, unspoken in formal papers, but whispered in hallway conversations. If 3I Atlas were somehow artificial, or at least influenced by artificial means, then controlled rotation would be possible. A sufficiently advanced technology could stabilize an object's spin, perhaps to maintain optimal solar orientation, or to prevent structural stresses. But this is speculation piled on speculation. To invoke artificial intervention, you'd need extraordinary evidence, and so far, all we have are anomalies. Puzzling, yes, but not necessarily indicative of artificiality. Science demands that natural explanations be exhausted first. Still, the rotation enigma gnaws at researchers. It's one more piece that doesn't quite fit, one more oddity in a growing list of oddities. By mid-October, as 3I Atlas continued its inward plunge, astronomers tried a different approach: radar. Radar observations can probe an object's shape, spin state, and surface roughness directly without relying on passive light. The Arecibo radio telescope, which would have been ideal, was lost in 2020. But other facilities like the Goldstone Deep Space Network antenna in California can sometimes detect asteroids and comets. Radar requires a strong transmitter and a sensitive receiver. The transmitted radio waves bounce off the object and return to Earth, carrying information about its distance, velocity, and surface properties. For a typical asteroid a few kilometers across, radar can detect it out to roughly 0.1 astronomical units, about 15 million kilometers. Beyond that, the signal becomes too weak. 3I Atlas in mid-October was still about 1.5 astronomical units from Earth, 10 times farther than the typical radar range. Detecting it would require not just a strong signal, but also a large reflective target. And if the nucleus is small and embedded in a diffuse coma, the radar return might be too faint to detect. Goldstone attempted observations anyway. On October 12 and 13, 2025, the 70-meter antenna transmitted toward 3I Atlas, then listened for the echo. The observations lasted several hours each night, covering multiple rotation periods if the object spun quickly. No echo was detected. This was disappointing, but not surprising. The distance was marginal, the target was small, and the coma might have scattered or absorbed the radar signal. The null result didn't rule out anything, but it didn't help either, and so the rotation question remained unanswered. Perhaps Atlas rotates, just too slowly or too uniformly to see. Perhaps the geometry is unfavorable. Perhaps the coma hides the nucleus too well, or perhaps the object's rotation has been suppressed by processes we don't yet understand. The facts are extraordinary enough, but the absence of rotation, or at least the absence of detectable rotation, adds another layer to the mystery, another anomaly, another reason to keep watching, keep measuring, keep wondering. Because as 3I Atlas closed in on perihelion, time was running out. The opportunity to solve this puzzle wouldn't last forever. Soon the object would swing past the sun, accelerate back toward the outer solar system, and fade from view. If answers were to be found, they'd have to be found soon. Beyond the missing acceleration, beyond the uniform temperature, beyond the rotation enigma, there's the question of identity. What exactly is 3I Atlas made of? And does its composition hold clues to the other mysteries? Spectroscopy is the key. By dissecting the light from the coma, astronomers can identify molecules and atoms with extraordinary precision. Each species leaves a unique fingerprint, a pattern of emission or absorption lines at specific wavelengths. Read the fingerprints, and you read the object's chemical story. By late October 2025, as 3I Atlas approached perihelion, multiple observatories had compiled extensive spectroscopic datasets. The Gemini South Telescope, the Very Large Telescope, VLT, the Keck Observatory in Hawaii, and even the Subaru Telescope had all contributed spectra across visible, ultraviolet, and near-infrared wavelengths. The molecular inventory was growing. Cyanogen, CN, diatomic carbon, C2, hydroxyl, OH, and carbon monoxide, CO, were confirmed. Weak signals hinted at ammonia, NH3, and methane, CH4, though these were at the edge of detectability. Sodium Na emission was present, likely from dust grains vaporizing in the intense sunlight as the object neared perihelion. And then there was the nickel. The nickel emission lines, first detected in early observations, persisted and even strengthened as the object approached the sun. The lines at 341.5 and 352.5 nanometers were clear and unambiguous. Nickel was there in the coma at measurable concentrations, but iron-nickel's geochemical twin remained conspicuously absent, or at least far weaker than expected. This was the smoking gun, the chemical anomaly that refused to resolve. Astronomers proposed several mechanisms to explain the nickel without iron puzzle. One idea involved selective vaporization. Nickel and iron have slightly different vapor pressures. Under certain conditions, specific temperatures, pressures, or chemical environments, nickel might vaporize preferentially, releasing into the coma while iron remains locked in solid grains. But the differences in vapor pressure are small. You'd need very precise conditions to fractionate nickel and iron so completely. Another hypothesis invoked mineralogy. Perhaps the dust grains in 3I Atlas are dominated by nickel-rich sulfides like pentlandite, which can have high nickel-to-iron ratios. If iron-bearing minerals like troilite or magnetite are rare or absent, the escaping vapor would be nickel-rich. But this requires a very specific mineral assemblage again, not impossible but unusual. A third possibility was photochemistry. Maybe iron is present in the coma, but bound in molecules that don't emit at observable wavelengths. For example, iron could be tied up in complex organics or iron carbonyls, which are difficult to detect spectroscopically. Nickel, being less reactive, might remain in atomic form, producing strong emission lines. This is plausible, but it's also speculative. There's no direct evidence for such molecules. Karen Meach, a planetary scientist at the University of Hawaii, commented in an October interview that the nickel signal was intriguing but not necessarily alarming. She noted that cometary chemistry is diverse and interstellar comets might have compositions reflecting their formation environments. If 3I Atlas formed in a region rich in nickel-bearing minerals, or if it underwent processing that depleted iron, we'd see exactly this kind of signature, she said. It's unusual, but unusual isn't the same as impossible. Meach's perspective was grounded and cautious, a counterbalance to more speculative interpretations. But even she acknowledged that the combination of the missing NGA and the odd chemistry was worth taking seriously. The spectral fingerprint also revealed information about isotopes. As mentioned earlier, deuterium to hydrogen, DH ratios, are key tracers of formation conditions. Water molecules containing deuterium emit at slightly different wavelengths than normal water. By comparing the strengths of these emissions, astronomers can estimate the DH ratio. Preliminary measurements from the VLT, conducted in late October, suggested a DH ratio of roughly 3x10⁴, 3 deuterium atoms for every 10,000 hydrogen atoms. This is higher than typical for solar system comets, which range from 1.5 × 10⁴ to 2.5 × 10⁴. The elevated DH ratio implies formation in a very cold environment, consistent with the outskirts of a protoplanetary disk, or even the cold molecular cloud from which the disk formed. In other words, 3I Atlas likely originated far from its parent star, in conditions even colder than the Kuiper belt. This aligns with its interstellar status. It's a wanderer from the frozen fringes of another stellar system. But here's the twist. The DH ratio, while elevated, isn't extreme. Some solar system comets, particularly those from the Oort cloud, have DH ratios approaching 3x10⁴, so 3I Atlas isn't wildly different. It's at the high end of the range, but still within the broader family of comets. This is both reassuring and frustrating. Reassuring because it suggests that comet formation is indeed a universal process, producing similar objects regardless of location. Frustrating because it means the chemistry alone doesn't explain the other anomalies. A high DH ratio doesn't make the NGA disappear. It doesn't stabilize rotation. It doesn't create nickel without iron. Spectroscopy also provided clues about the dust. Scattered sunlight from dust grains produces a continuum, a smooth background of light across all wavelengths, lacking the sharp features of molecular emission. By measuring this continuum, astronomers can estimate the amount and size distribution of dust. 3I Atlas's continuum was weak, confirming earlier findings that the coma is gas-dominated. The dust-to-gas ratio appeared to be around 0.1 to 0.3 by mass, meaning for every kilogram of gas, there's only 100 to 300 grams of dust. This is lower than typical comets, which often have dust-to-gas ratios near 1 or higher. Low dust production is consistent with a relatively clean, icy surface. It suggests that the object's nucleus isn't heavily mantled in refractory material, dust and rocks that insulate the ice and suppress outgassing. Instead, the surface is likely fresh, exposed ice, sublimating efficiently in the sun's heat. But if the surface is fresh, why is the outgassing so symmetric? Exposed ice should create localized jets wherever sunlight strikes, unless again the entire surface is uniformly icy, a perfectly clean, perfectly smooth coating of volatiles. Possible? Technically. Plausible? That's the recurring question. Another spectroscopic observation came from the Atacama Large Millimeter Array, ALMA, in Chile. ALMA, a network of radio telescopes, is exquisitely sensitive to molecular line emission in the millimeter and sub-millimeter wavelengths. It can detect molecules like hydrogen cyanide, HCN, methanol, CH3OH, and formaldehyde, H2CO species that are difficult or impossible to observe at optical wavelengths. ALMA observed 3I Atlas on October 18th and 19th, 2025, targeting HCN emission at 3 millimeters. HCN is a tracer of complex organic chemistry, common in comets and interstellar clouds. Its presence would indicate that 3I Atlas harbors organic molecules beyond the simple CN and C2 already detected. The observations succeeded. ALMA detected a clear HCN signal, confirming that 3I Atlas contains complex organics. The HCN production rate was modest, around 1025 molecules per second, but measurable. This placed the object in the middle range of cometary activity, neither particularly active nor particularly dormant. What ALMA didn't detect was equally important. No methanol, no formaldehyde, no sulfur-bearing molecules like sulfur dioxide, SO2, or hydrogen sulfide, H2S. The non-detections suggested that either these species are rare in 3I Atlas or they're present in concentrations below ALMA's sensitivity. The lack of sulfur compounds is interesting. Sulfur is moderately abundant in comets, often appearing as SO2 or CS2. Its absence might indicate a depletion, perhaps due to loss during the object's long journey through interstellar space. Sulfur compounds are volatile and can be destroyed by cosmic rays and UV radiation over millions of years. If 3I Atlas has been wandering for a very long time, it might have lost much of its sulfur. Alternatively, the object's formation environment might have been sulfur-poor. Not all regions of protoplanetary disks have the same elemental abundances. Variations in temperature, pressure, and chemistry can lead to localized depletions or enrichments. A sulfur-poor birthplace would naturally produce a sulfur-poor comet. The spectral fingerprint taken as a whole paints a picture of an object that's chemically diverse but not exotic. It has water, carbon compounds, hydrogen cyanide, and metals, all ingredients found in solar system comets. The differences are subtle: slightly elevated DH, slightly low dust, nickel without iron, subdued sulfur. Each difference is small, but together they add up to something distinctive. It's like listening to a familiar song played in a slightly different key. The melody is recognizable, but something feels off. You can't quite put your finger on it, but you know it's not the original. And beneath the chemistry lies the dynamical puzzle. Because no matter how you interpret the spectra, the fact remains: the object is outgassing, but not accelerating. The chemistry doesn't change that. It doesn't make the physics go away. As perihelion approached less than 2 weeks away now, the spectroscopic campaigns intensified. Every clear night, telescopes pointed at 3I Atlas, recording spectra, monitoring emission lines, searching for changes. The data poured in, filling hard drives, fueling papers, and deepening the enigma. The facts are extraordinary enough, but the spectral fingerprint, for all its detail, offers no resolution. Only more questions. By late October 2025, with perihelion just days away, one hypothesis had gained traction among researchers. Perhaps the outgassing is indeed symmetric, balanced to such a degree that momentum vectors cancel out almost perfectly. If true, this would explain the missing NGA without invoking exotic physics or artificial intervention. But could nature achieve such symmetry? The hypothesis requires several conditions. First, the nucleus must be either spherical or at least very regular in shape, minimizing geometric asymmetries. Second, The surface composition must be uniform so that all areas outgas at similar rates when heated. Third, the rotation must be either very slow or aligned such that solar heating is distributed evenly over time. Fourth, there can be no dominant jets or localized vents. Outgassing must emerge from across the entire surface. Each condition individually is rare. Together, they're extraordinarily unlikely but not impossible. Let's consider spherical nuclei. Gravity naturally shapes large bodies into spheres. The Earth, the Moon, Jupiter, all are roughly spherical because gravity pulls matter toward the center, smoothing out irregularities. But gravity becomes effective only above a certain size, typically a few hundred kilometers in diameter. Below that threshold, objects are too small for self-gravity to overcome material strength. They remain irregular, shaped by collisions and accretion rather than gravitational collapse. At 4 to 5 kilometers across, 3I Atlas is well below the threshold for gravitational rounding. It should be lumpy, like an asteroid or a small comet. Nucleus. To be spherical at this size would require either formation under unusual conditions, perhaps slow, gentle accretion in a very cold, low-turbulence environment, or subsequent reshaping, perhaps through prolonged outgassing that eroded away irregularities. Neither scenario is well supported. Slow, gentle accretion might produce less irregular shapes, but perfect spheres remain unlikely. Erosion by outgassing can smooth surfaces, but comets typically lose material unevenly, creating new irregularities even as they erase old ones. Comet 67P, for instance, became more irregular over time as cliffs collapsed and pits formed, so spherical shape, possible but improbable. Next, uniform composition. Comets are heterogeneous. They're made of ice, dust, and rock mixed together in varying proportions. Some regions are ice-rich, others dust-rich. This heterogeneity arises from the accretion process comets form from collisions and sticking of smaller particles, each with slightly different compositions. The result is a patchwork, not a uniform block. For 3I Atlas to have uniform composition, it would need to have formed from a very homogeneous source material or undergone processing that mixed and blended its interior. Thermal processing internal heating from radioactive decay or tidal forces can cause melting and differentiation, creating layers. But small comets like 3I Atlas lack the mass to retain significant heat. Radioactive decay is minimal, and tidal heating requires close approaches to massive bodies, which an interstellar object wouldn't experience often. Alternatively, maybe the surface is uniformly mantled in a layer of processed material tholins, for instance, that insulates the interior and regulates outgassing. A mantle could create apparent uniformity even if the interior is heterogeneous, but mantles typically form through prolonged solar heating, not during interstellar travel. And if 3I Atlas has a thick mantle, why is it outgassing so vigorously? Uniform composition, again possible but improbable. Third, the rotation. We've already discussed the rotation enigma. If the rotation is slow, say, once every several days, then different parts of the surface would remain in sunlight for extended periods, allowing for more uniform heating. This might reduce asymmetries in outgassing. But even slow rotation doesn't guarantee symmetry unless the shape and composition are also uniform. Alternatively, if the rotation axis points toward or away from the Sun, the same hemisphere would face the Sun continuously, much like the Moon's tidal lock with Earth. This is called a spin-Sun resonance, and it can happen if tidal forces or outgassing torques have damped the rotation into a specific configuration. But achieving such a resonance requires fine-tuning, and it's unclear what mechanism could have driven 3I Atlas into this state during its interstellar journey. Rotation. Possible under specific conditions, but again, improbable, without additional mechanisms. Fourth, distributed outgassing. This is perhaps the most plausible condition. If the nucleus has a porous, sponge-like structure, what's called a rubble pile, then gas generated in the interior could percolate through interconnected voids, emerging from many small openings across the surface. This would naturally distribute the outgassing, preventing localized jets. Rubble pile structures are common in asteroids and are thought to exist in some comets. Comet 67P, for instance, showed signs of being a contact binary, two lobes stuck together, possibly a rubble pile on a larger scale. If 3I Atlas is a rubble pile, gas could flow through the porous matrix, escaping in all directions. But even rubble piles aren't perfectly symmetric. Porosity varies from place to place. Some pathways are more open than others. You'd still expect some asymmetry, some regions where gas escapes more readily. Achieving near-perfect balance remains difficult, so the symmetry hypothesis requires stacking several low-probability conditions: spherical shape, uniform composition, favorable rotation, and distributed outgassing. Individually, each is conceivable. Together, they form a scenario that's statistically unlikely. But unlikely isn't impossible. Could stability this perfect really be natural? Some researchers argue that we're dealing with selection bias. Interstellar objects are rare, and we've only detected 3. Maybe highly symmetric, non-accelerating objects are actually common, but we've just been unlucky with our small sample size. In other words, perhaps 3I Atlas represents a class of objects we haven't appreciated yet, ancient, processed, homogenized bodies that wander the galaxy in states of near equilibrium. This is a fair point. Our understanding of interstellar objects is in its infancy. We can't rule out the existence of unusual subpopulations, but even if such objects exist, we still need to explain how they achieved their properties. Symmetry, uniformity, and stability don't arise spontaneously. They require specific formation or evolutionary pathways. Another angle involves the role of ice layers. Suppose 3I Atlas underwent a phase of intense heating in its past, perhaps a close encounter with a hot star, or an episode of internal heating from short-lived radioisotopes. The heating could have melted and refrozen surface ices, creating a smooth, uniform coating. This coating would then sublimate evenly when exposed to the sun, producing symmetric outgassing. But intense heating events are rare and would likely alter the object's orbit or composition in detectable ways. And the DH ratio suggests formation in a very cold environment, not a hot one. If 3I Atlas experienced significant heating, you'd expect isotopic fractionation or loss of volatiles, signs that aren't strongly present. The symmetry hypothesis is appealing because it stays within the bounds of known physics. It doesn't require invoking new phenomena or questioning established laws, but it does require accepting a confluence of rare conditions, a cosmic coincidence that many find uncomfortable. In science, coincidences are sometimes real. The universe is vast and rare events happen, but they're also red flags. When a single explanation requires too many coincidences, it's worth asking if there's a simpler alternative, even if that alternative is unsettling. As 3I Atlas approached perihelion on October 30th, 2025, the symmetry hypothesis remained on the table. It was neither proven nor disproven, hanging in the balance alongside other explanations. Researchers continued to debate, to model, to calculate the odds. And in the back of many minds, a question lingered. What if symmetry isn't the answer? What if there's something else going on, something we haven't considered because it falls outside the usual boundaries of natural phenomena? The facts are extraordinary enough, but the symmetry hypothesis, for all its appeal, doesn't fully satisfy. It explains the observations, but barely. It fits the data, but only if you squint. And as perihelion arrived, the moment of maximum activity and brightest visibility, the world's telescopes watched, hoping the object might reveal its secrets at last. October 30th, 2025, perihelion. At 14:23 UTC, 3I Atlas reached its closest point to the Sun, 1.4 astronomical units, or about 210 million kilometers. For reference, that's slightly beyond the orbit of Mars, which averages 1.52 AU. The object was still far from the Sun by inner solar system standards. Earth orbits at 1 AU, Venus at 0.72 AU, Mercury at just 0.39 AU. But for a comet, 1.4 AU is close enough to drive vigorous outgassing. Astronomers around the world watched. Observatories in Chile, Hawaii, the Canary Islands, Arizona, South Africa, All pointed their instruments at the visitor. Hubble and JWST observed from space. Amateur astronomers with large backyard telescopes scanned the sky, hoping to catch a glimpse. The object brightened to magnitude 15.8, still too faint for casual observation, but within reach of serious amateurs with 12-inch or larger telescopes. The coma expanded slightly, now spanning nearly 60,000 kilometers. The tail, previously faint, became more pronounced, stretching about 100,000 kilometers in the anti-sunward direction. But there were no outbursts, no sudden flares, no dramatic changes. The activity remained steady, predictable, almost serene. It was as if perihelion, the moment when most comets become most active, most chaotic, was just another day for 3I Atlas. Spectroscopy at perihelion showed intensified emission lines. The CN and C2 features brightened, indicating increased outgassing. Water production, inferred from OH emission, roughly doubled compared to September levels, consistent with the increased solar heating. The nickel lines persisted, strong and clear. The thermal glow, measured by JWST, peaked at around 270 Kelvin, still surprisingly uniform across the coma. Orbital tracking continued, now with even higher precision. With the object at its brightest and closest, positional measurements were more accurate than ever. The data poured into dynamical models, refining the trajectory. And the result? Still no measurable non-gravitational acceleration. If anything, the perihelion data made the absence of NGA even more striking. This was the moment when outgassing should be strongest, when recoil forces should be most apparent, yet the orbit remained purely gravitational, following Newton and Kepler with flawless precision. Some researchers had hypothesized that perhaps the NGA was weak before perihelion, but would become detectable near or after perihelion when the object was most active. The perihelion observations ruled that out. The NGA, if it existed, was below 1x10 to 8 MES2, 100 times weaker than 2I Borisov's. This was now beyond unusual. It was borderline inexplicable. On October 31st, the day after perihelion, a team of astronomers from the European Southern Observatory, ESO, released a preliminary analysis of VLT spectroscopy. The paper, posted to the Archive preprint server, summarized months of observations and modeling. The conclusions were cautious, but pointed. 3I 2025 F1 Atlas exhibits cometary activity consistent with sublimation of volatile ices, yet displays no detectable non-gravitational acceleration within current observational limits. This combination of properties is unprecedented and challenges our understanding of cometary dynamics. While several hypotheses have been proposed, including highly symmetric outgassing, unusually high mass, or novel internal structures, none fully account for the observations without invoking low probability conditions. Further observations and theoretical modeling are urgently needed. The paper avoided speculation about artificial origins, sticking strictly to observational facts, but its concluding sentence was telling: "The nature of 3I Atlas remains an open question, and we encourage the community to consider all physically plausible explanations." Translation: we're stumped, and we're open to ideas. The ESO paper sparked a flurry of activity. Within days, follow-up papers appeared, each proposing new models or reanalyzing existing data. Some argued for rubble pile structures with extreme porosity. Others invoked exotic ices with unusual sublimation properties. A few revisited the possibility of extremely low albedo and correspondingly high mass. But none of the models were entirely convincing. Each required assumptions that were difficult to justify, or parameters that were poorly constrained. The models fit the data, technically, but they felt forced, like trying to fit a square peg into a round hole by shaving off the corners. Meanwhile, as 3I Atlas began its outbound journey, moving away from the Sun and toward the outer solar system, the observing window began to close. The object was still bright enough for follow-up, but it was fading. Predictions suggested it would drop below magnitude 20 by mid-November and below magnitude 22 by December. After that, only the largest telescopes would be able to track it. Time was running out. On November 3rd, 2025, 3I Atlas passed within 1.7 astronomical units of Earth, its closest approach to our planet. This was an opportunity for radar observations, though the distance was still marginal. Goldstone tried again, transmitting powerful pulses toward the object. This time, there was a faint return signal. It was weak, barely above the noise, but it was there. The signal suggested a solid nucleus as expected, with a radar cross-section consistent with a body a few kilometers across. The echo's polarization properties hinted at a rough surface, typical of comets and asteroids. No shocking revelations, but at least confirmation that there was indeed a solid object at the heart of the coma. More importantly, the radar data allowed for a direct measurement of the object's distance and velocity, independent of optical tracking. When combined with optical astrometry, this improved the orbit determination even further, and still no NGA. The radar observation was the last major dataset collected before the object began to fade. From here on, observations would be more difficult, more sparse. The golden window from discovery in March through perihelion in October was closing, but the mystery remained wide open. Perihelion had been the test, the moment of truth, and 3I Atlas had passed. Through it, with the same enigmatic calm it had shown all along. No outbursts, no rotation signals, no measurable acceleration, just steady, symmetric, persistent activity. In a way, the lack of drama was itself dramatic, because normal comets are chaotic. They surprise you. They erupt, they fragment, they spin wildly. They follow the rules of physics, but they do so messily, unpredictably. 3I Atlas was different. It followed the rules, some of them, but with an orderliness that felt wrong. Too neat, too controlled. And that orderliness, that refusal to behave like a typical comet, was what kept astronomers awake at night. The facts are extraordinary enough, but the perihelion passage, for all the data it provided, offered no resolution. Only confirmation that whatever 3I Atlas is, it's playing by a rulebook we don't fully understand. November 2025. The show was ending. As 3I Atlas receded from the sun, moving back toward the outer solar system, its brightness began to decline. By early November, the object was visibly dimmer. Each passing night the light faded further. The coma shrank. The dust tail, previously faint but detectable, grew even fainter, blending into the background glow of distant stars. This is the natural life cycle of every comet's apparition. They approach, brighten, reach peak activity, then fade. It's a rhythm astronomers have witnessed countless times, and as comets fade, so does our ability to study them. Observations become harder, details blur. Eventually the comet disappears into the cosmic darkness, indistinguishable from the millions of faint points scattered across the sky. For 3I Atlas, this fade meant something more profound, the end of the investigation. The object wouldn't return. Its trajectory guaranteed a one-way journey out of the solar system, back into the void between stars. Humanity had been given one pass, one chance to understand this visitor, and that chance was slipping away. But even as the object dimmed, astronomers refused to look away. Every additional observation mattered. Every spectrum, every image, every measurement of position added another piece to an incomplete puzzle. Because even if the mystery couldn't be solved now, perhaps future researchers decades from now, with better tools and deeper knowledge, might find answers hidden in this archive. By mid-November, 3I Atlas had faded significantly. Professional telescopes could still track it, but the object was now at the edge of visibility even for large instruments. The window was closing. On November 15th, the James Webb Space Telescope conducted its final observation. JWST's infrared instruments pointed one last time at the retreating visitor, capturing thermal signatures and molecular emissions. The data showed a coma still slightly warmer than expected for an object at that distance, but cooling rapidly. The carbon monoxide signal, previously detectable, was now weaker. The dust continuum had diminished. The object was shutting down, returning to dormancy. Hubble followed a week later, taking a final series of images. The coma was now barely visible, a faint smudge against the star field, like breath on a cold window, slowly evaporating. The nucleus itself remained invisible, too small and too dark to resolve, buried somewhere within that fading glow. Ground-based observatories continued their vigil as long as conditions allowed. The Very Large Telescope in Chile, Gemini South, the Keck Observatory in Shimoisetsun, Hawaii, Subaru in Japan, all captured final spectra in late November and early December. Each observation was precious, a last chance to record something that might have been missed. By the second week of December, 3I Atlas had faded beyond the reach of most telescopes. Only the largest instruments under perfect conditions could still detect it. The object was now just another faint point in a sea of faint points. On December 22nd, the Minor Planet Center issued its final update. The E object was now moving at roughly 31 kilometers per second, relative to the Sun, heading outward toward the constellation Eridanus, the same direction from which it had arrived. The updated orbit, incorporating every measurement from discovery in March through the final observations in December, confirmed what had been known since spring. The trajectory was hyperbolic, definitively unbound. 3I Atlas would never return. In a few years, it would cross the orbit of Pluto. In a few decades, it would pass beyond the Kuiper Belt. In a century, beyond the heliopause, the edge where the Sun's influence fades and true interstellar space begins. And then, silence. The object would resume its journey through the galaxy, one more wanderer among billions, drifting through the darkness for millions of years. But the data remained. Thousands of images, hundreds of spectra, millions of individual measurements, a vast archive of information, meticulously recorded and preserved. In the weeks following the final observations, research groups around the world began compiling their findings. Papers were drafted, analyses refined, conclusions debated. The object might be gone, but the investigation continued. If there was a consensus, and consensus is always fragile in science, it was this: 3I Atlas is anomalous. It doesn't fit cleanly into existing categories. It challenges assumptions about how comets behave. And while natural explanations remain possible, perhaps even probable, they all require stacking conditions that are individually plausible but collectively improbable. Some researchers doubled down on the symmetry hypothesis, arguing that with enough fine-tuning, a natural object could achieve the properties observed. They pointed to the absence of any clear technological signatures, no radio signals, no geometric structures, no obvious artificial patterns. Others remained skeptical. They noted that absence of evidence isn't the same as evidence of absence. Just because we haven't detected artificial signals doesn't mean they aren't there. Perhaps the object is passive, designed to appear natural, or perhaps we simply haven't looked in the right way, at the right wavelengths, with the right assumptions. A third group proposed a middle path. Perhaps 3I Atlas represents a class of objects we haven't recognized yet. Ancient bodies that have spent billions of years wandering through interstellar space, subjected to processes we don't fully understand. Cosmic rays, starlight, interstellar dust over eons. These forces could transform an object, creating properties that seem unusual by solar system standards. But even this moderate interpretation required speculation. The processes are poorly understood. The timescales are vast. The evidence is circumstantial. And so the debate continued, unresolved. One intriguing development emerged in early December. A team at MIT reanalyzed the complete orbital data set using advanced statistical methods. They asked a specific question: could there be a very small non-gravitational acceleration so tiny it's buried in measurement noise that previous analyses missed? The answer was tentative. Maybe. The analysis suggested a possible acceleration about 5 times smaller than the formal detection threshold. The signal was weak, marginal, sitting right at the edge of statistical significance. It could be real. It could be noise. The uncertainty was too large to be sure. If real, even this minuscule acceleration would still be extraordinarily small, roughly 100 times weaker than what 2I Borisov exhibited. Producing such a tiny push would require either exceptionally weak outgassing, implausibly high mass, or near-perfect symmetry with just the slightest imbalance. The MIT team emphasized caution. Their paper stated clearly that the result was tentative, that independent confirmation would be necessary. But by the time the paper was released, 3I Atlas was already too faint for follow-up. Observations. The moment had passed. The tentative detection was both tantalizing and frustrating. If true, it meant the object wasn't perfectly symmetric after all, just very, very close. But if false, it was nothing more than a pattern glimpsed in noise, a mirage in the data. Either way, the central mystery remained. Even with a barely detectable acceleration, the object was still profoundly anomalous. The ratio between visible activity and measurable dynamics was far outside anything seen before. As December turned into January 2026, public interest in 3I Atlas began to wane. The object had faded from view, both literally and figuratively. News outlets moved on. Social media shifted focus. The viral excitement about the mysterious interstellar visitor gave way to other sensations, other stories. But within the scientific community, interest remained intense. Research groups continued analyzing data. Models were refined. Papers were published. The object might be gone, but its legacy endured. And for those researchers who had spent months tracking the visitor, who had sacrificed sleep, rearranged schedules, fought for telescope time, the fade brought mixed emotions. Relief that the frantic pace was over. Regret that the mystery remained unsolved. 3. Atlas had offered a glimpse of something beyond our understanding, and now it was gone, receding into darkness, leaving behind only questions and data. The facts are extraordinary enough, but as the object disappeared, realization settled in. We might never know the full truth. The universe had presented a puzzle and humanity had done its best, but the universe, as always, kept some secrets to itself. Perhaps someday another visitor will arrive, one easier to explain or harder to dismiss. Perhaps future instruments will detect objects like this earlier, track them longer, probe them deeper. Or perhaps 3I Atlas will remain unique, a singular anomaly that defies all attempts at categorization. Only time will tell. And for this particular visitor, time had run out. With 3I Atlas now beyond reach, astronomers turned to comparison. What could be learned by examining this object alongside the only two other confirmed interstellar visitors, 1I Oumuamua and 2I Borisov? Perhaps by looking at all three together, patterns might emerge. Commonalities might illuminate what interstellar objects are. Differences might reveal what makes each unique. But the comparison revealed something unsettling. The three objects were strikingly different from one another. 1I Oumuamua arrived first in October 2017. It remains the most enigmatic. Discovered after it had already passed closest to the Sun, Oumuamua was outbound when astronomers spotted it. Its hyperbolic orbit proved immediately that it came from beyond our solar system, a visitor from another star. Its appearance was unusual. Elongated, possibly shaped like a cigar, or perhaps a flat disk. It tumbled chaotically through space, its brightness flickering as it rotated. Spectroscopy revealed nothing, no cometary emissions, no molecules, no gases. It appeared inert, dormant. Yet as it receded from the Sun, something unexpected happened. It accelerated. Not by much, just a few millimeters per second every second, but measurably, definitively. The acceleration was real. This created a paradox. Comets accelerate when they outgas, but Oumuamua showed no signs of outgassing, no coma, no tail, no molecular signatures. Yet the acceleration was there, undeniable in the data. Explanations proliferated. Some researchers proposed that Oumuamua released pure hydrogen gas, so transparent it wouldn't produce a visible coma. Others suggested it might be a fragment of a shattered planet, outgassing some exotic substance we couldn't detect. A few, including Abraham Loeb at Harvard, proposed something more radical. Perhaps it was a thin, reflective sheet, a light sail pushed by solar radiation pressure, rather than outgassing. The light sail hypothesis was controversial, pushing at the boundaries of mainstream science. But it couldn't be definitively ruled out. The data fit. The idea was physically possible, if technologically extraordinary. Then came 2I Borisov in August 2019. Unlike Oumuamua, Borisov was unambiguously a comet. It had everything you'd expect: a bright coma, a dust tail, strong spectral signatures of familiar molecules, water vapor, carbon monoxide, cyanogen, all present, all behaving exactly as solar system comets behave. Its composition resembled our comets closely. The chemistry, the dust properties, the outgassing patterns all fell within familiar ranges. And crucially, Borisov showed measurable non-gravitational acceleration, entirely consistent with its observed activity. Borisov played by the rules. It was comforting in a way. After the strangeness of Oumuamua, Borisov offered reassurance. Comets form similarly across the galaxy. The universe makes sense. Then came 3I Atlas, and with it, a new kind of paradox. Unlike Oumuamua, 3I Atlas had a visible coma. It showed clear spectroscopic evidence of outgassing. It looked like Borisov, behaved like a comet in almost every visible way. But unlike both Oumuamua and Borisov, it showed no clear non-gravitational acceleration, or at best, an acceleration so small it was buried in measurement noise. It was as if someone had taken Borisov's appearance and Oumuamua's dynamical mystery, then fused them in the most confounding way imaginable. Consider the pattern. Oumuamua, acceleration without visible activity. Borisov, activity with expected acceleration. 3I Atlas, activity without expected acceleration. Each visitor broke the pattern in a different way. Each defied expectations uniquely. Together, they suggested something profoundly unsettling. Interstellar space might harbor far more diversity than our theories anticipated. Some researchers proposed that the differences reflected different origins. Perhaps Oumuamua formed close to its parent star, in a region where rocky or metallic bodies dominated. Borisov formed farther out, in icy zones similar to our Kuiper belt. And 3I Atlas. Perhaps it originated even farther, in the frigid outer reaches where ices underwent long-term processing under starlight and cosmic rays. This formation gradient idea was plausible for chemistry. Different environments produce different compositions, but it struggled to explain the dynamical oddities. Why would formation location affect whether outgassing produces acceleration? That's a question of physics, not birthplace. Another idea focused on evolutionary pathways. Perhaps all three started as typical comets, but evolved differently during their interstellar journeys. Oumuamua might have been heavily processed, losing volatiles, becoming dense and rocky. Borisov remained pristine, barely altered. 3I Atlas might have undergone transformation that homogenized its structure, creating symmetry. But what transformation? Cosmic. Rays alter surfaces, but don't reshape entire bodies. Collisions are rare in the emptiness between stars. Internal heating from radioactive decay is weak in small objects and fades over time. No single process explained all three. A more humbling possibility emerged in private discussions. Perhaps we're simply working with too small a sample. 3 objects. That's all we have. Trying to understand the diversity of interstellar visitors from 3 examples is like trying to understand Earth's biology by examining a platypus, a giraffe, and an octopus. You'd find patterns, perhaps, but they'd be misleading. This is the problem of selection bias. We detect only what's bright enough, close enough, moving through monitored regions of sky. The typical interstellar object, if such a thing exists, might be passing through unnoticed, too faint or too fast to spot. Estimates based on the 3 confirmed detections suggest several interstellar objects larger than 100 meters cross Earth's orbit every year. Most go unnoticed. We see only the exceptions, the ones bright enough, close enough, lucky enough to be caught. If the ones we do see are this strange, what about the ones we miss? The comparison revealed no clear answers, but it reframed the mystery. 3i Atlas isn't an isolated anomaly, it's part of a pattern of anomalies. Interstellar objects, it seems, resist categorization. Each one challenges assumptions, each one forces expansion of our thinking. Perhaps that's the real lesson. The universe is more diverse, more surprising, more creative than our models anticipate. Every time we think we understand comets, asteroids, or visitors from beyond, nature reveals something unexpected. And with only 3 examples, we're still at the very beginning of understanding what wanders through the space between stars. The facts are extraordinary enough, but the comparison suggests something deeper. We're scratching the surface, and with better surveys, better instruments, and perhaps a bit more luck, we might discover just how strange and how common interstellar visitors truly are. Even as 3i Atlas faded beyond detection, its observational legacy endured. The months of intensive study from March through December 2025 represented one of the most comprehensive investigations of an interstellar object ever undertaken. The sheer volume of data was staggering. This archive would become a resource for decades. Future researchers, equipped with better computational tools and deeper theoretical understanding, might extract insights that current analysts overlooked. Hidden patterns might emerge years from now. Questions might find answers long after the object itself has vanished. One immediate legacy was technical. Tracking 3i Atlas pushed observational astronomy to its limits. New methods were developed for extracting faint signals from noisy backgrounds. Spectroscopists refined techniques for detecting weak molecular emissions. Orbital analysts improved algorithms for modeling trajectories with minimal assumptions. These advances rippled outward, benefiting all of planetary science. Better tools for studying faint comets, better techniques for predicting asteroid orbits, better methods for characterizing distant, barely visible objects. The campaign to understand one mysterious visitor improved how we study everything else. Another legacy was collaborative. The global effort observatories on 6 continents, space telescopes, amateur astronomers, international data-sharing networks demonstrated what the astronomical community could achieve when united by a compelling target. Rivalries were set aside, data flowed freely between institutions. Telescope time was allocated generously, with competing groups coordinating rather than competing. It was science at its best, cooperative, open, driven by curiosity rather than competition. This spirit extended to public engagement. Throughout the apparition, astronomers communicated regularly with journalists and the wider public. Press releases explained discoveries in accessible language. Social media threads demystified the science. Some observatories even live-streamed observations, allowing anyone with an internet connection to watch telescopes tracking the visitor in real time. Millions followed the story. Even those who couldn't see the object through their own telescopes felt connected to the investigation. It was a reminder that science isn't confined to laboratories and institutions. It's a human endeavor, driven by wonder, open to all who care to look up. But perhaps the most profound legacy was conceptual. 3i Atlas forced astronomers to confront the limits of their understanding. It challenged fundamental assumptions about cometary behavior, about the relationship between activity and dynamics, about what qualifies as normal in the cosmos. Questions that once seemed settled were reopened. Can a comet outgas without producing measurable acceleration? Under what conditions might that occur? Are there classes of objects, natural classes, that we simply haven't recognized yet because our sample size is too small? These questions drove new research proposals. Teams sought funding for laboratory experiments, studying exotic ice structures and sublimation under unusual conditions. Theorists proposed modeling porous rubble pile nuclei to understand how distributed outgassing might work. Observers requested time on existing surveys and proposed building new ones, dedicated to detecting interstellar objects as early as possible. One particularly ambitious proposal gained traction: a dedicated early warning system for interstellar visitors, a network of wide-field telescopes scanning the sky continuously, designed specifically to catch incoming objects within days of entering the inner solar system. With earlier detection, future visitors could be studied far more thoroughly. Spacecraft missions might even become feasible fast. Flyby probes launched quickly, reaching the visitor before it departs. The technology exists. The challenge is readiness. The proposal attracted serious interest from funding agencies. The 3I Atlas campaign had proven that the community was prepared, that global coordination was possible, that the science was compelling. Building such a system would take years, perhaps a decade, but the groundwork was being laid. In the meantime, existing surveys would carry the burden. Atlas, Pan-STARRS, the Vera Rubin Observatory all would watch for the next visitor, and eventually, inevitably, another would come. The archive also included a growing body of published research. By early 2026, more than 30 papers on 3I Atlas had appeared in peer-reviewed journals or preprint servers. Topics ranged from orbital mechanics to molecular spectroscopy to theoretical models of cometary interiors. Each paper added a piece to the puzzle, even if the full picture remained incomplete. Some papers were conservative, focusing strictly on observations. Others explored unconventional ideas, testing hypotheses at the edge of current understanding. The diversity of approaches was healthy. Science thrives on multiple perspectives, on respectful debate and creative tension. One particularly notable paper appeared in Nature Astronomy, titled simply 3I Atlas, Context and Implications. It synthesized months of observations, compared the object to Oumuamua and Borisov, and carefully discussed possible explanations for its anomalous properties. The conclusion was measured but striking. While natural processes can in principle account for individual features of 3I Atlas, the combination of properties challenges conventional models. We recommend continued vigilance for similar objects and encourage exploration of alternative frameworks, including those involving processes not yet incorporated into standard cometary physics. Extraordinary observations demand serious, open-minded investigation. The phrasing was careful, almost diplomatic. It didn't assert anything radical, but it opened the door, suggesting that perhaps our understanding of what's possible, what's natural, what exists out there, might need expansion. The paper sparked discussion. Some praised its balanced approach. Others felt it gave too much credence to speculative ideas. The debate was vigorous but remained respectful, a sign that the community was grappling seriously with uncomfortable questions. For the public, the legacy of 3I Atlas was more visceral. It reminded people that space isn't empty, that the universe is dynamic and full of surprises. It rekindled interest in exploration, in the search for life, in fundamental questions about our place in the cosmos. If an object this strange can drift through our solar system, what else is out there? What other mysteries pass unnoticed? What wonders await discovery? And for the researchers who dedicated months to this investigation, who lost sleep, rearranged lives, fought for every data point, the legacy was deeply personal. They had witnessed something rare, something unprecedented. They had been part of a story that might be remembered long after they're gone. Whether 3I Atlas was a natural oddball, a cosmic fluke, or something more, it had touched their lives. It had reminded them why they became scientists in the first place, to explore the unknown, to seek truth, to stand at the edge of human knowledge and peer into the key. Darkness beyond. The facts are extraordinary enough, but the legacy extends beyond facts and data. It's a legacy of curiosity, of persistence, of the human need to understand. And that legacy will endure long after the object itself has faded into the infinite night. As the initial wave of observational papers subsided, a handful of researchers began exploring more speculative territory. If conventional explanations felt insufficient, if natural mechanisms struggled to account for all the anomalies simultaneously, then what alternative frameworks deserved consideration? This is uncomfortable ground for science. Speculation can inspire breakthroughs, but it can also lead down blind alleys. The line between creative thinking and wishful thinking is thin. Yet sometimes pushing at the boundaries is necessary. Sometimes asking uncomfortable questions opens unexpected doors. One idea, discussed quietly at first and then more openly, involved the possibility of encoded information. The hypothesis was tentative, almost hesitant. What if 3I Atlas isn't simply an object but a carrier? The reasoning went something like this. Suppose an advanced civilization wanted to transmit information across interstellar distances. Traditional methods, radio signals, laser pulses, have drawbacks. They spread out over distance, weakening rapidly. They require precise targeting, and they're detectable by anyone monitoring that region of space. But physical objects, probes, packages, carefully designed artifacts could travel between stars carrying data. If designed to resemble natural comets, such objects might pass through other star systems without drawing attention. They'd appear mundane, ordinary. Only the intended recipient, equipped with the right tools or knowledge, would recognize the message. The coma's behavior, the spectral signatures, even the trajectory, all could theoretically encode patterns. Brightness fluctuations might follow sequences. Molecular emission lines might vary in ways that aren't random. The geometry of the coma might contain structure invisible to casual observation. To observers without the decryption key, the object would look natural. To those who knew what to look for, it might be a library. This idea, sometimes called the masked signal hypothesis, is highly speculative, but it's not entirely implausible. Humanity itself has sent physical messages into space. The Pioneer plaques, the Voyager golden records, proposals for interstellar probes, carrying data archives. If we can conceive such ideas within a century of spaceflight, what might civilizations millions of years older achieve? The hypothesis could, in theory, explain some oddities. The missing acceleration? Perhaps the outgassing isn't propulsive. It's deliberate, controlled, designed to create patterns without altering trajectory. The symmetric coma, engineered for uniformity, ensuring visibility from all angles. The stable activity, a programmed sequence, executed with mechanical precision. But the hypothesis faces steep challenges. First and most obviously, there's no evidence of encoded information. Researchers have analyzed brightness variations, spectral features, spatial structures. No patterns have emerged, no repeating sequences, no obvious modulation. Everything looks random, natural. Second, why disguise the message as a comet? If the goal is communication, why not make it obvious? A geometric structure, a radio beacon, an orbit with mathematical significance, these would attract immediate attention. Camouflaging a message seems counterproductive unless stealth is the objective. Third, if the object is artificial, it mimics nature extraordinarily well. The molecules detected cyanogen, diatomic carbon, hydroxyl form naturally in cometary ices. The isotope ratios are consistent with cold formation environments. The dust properties match expectations. Faking all these details would require profound sophistication. Proponents of the hypothesis argue that these objections miss a key point. Perhaps the message isn't meant for us. Perhaps humanity is eavesdropping on a conversation between distant civilizations, intercepting a transmission never intended for our eyes. In that case, the patterns might be encoded in ways we don't recognize. Wavelengths we're not monitoring, timescales we're not watching, mathematical frameworks we haven't considered. It's like overhearing a language you've never encountered. You detect sound, but you don't perceive meaning. This reasoning is difficult to refute because it's unfalsifiable. If the encoding is beyond our detection, then of course we won't detect it. But unfalsifiable hypotheses are problematic in science. They can't be tested, can't be proven or disproven. They exist in a realm beyond empirical investigation. A more focused version of the hypothesis examines the nickel anomaly. What if the nickel without iron signature is intentional? Nickel emission lines are distinctive, unmistakable in spectroscopy. If you wanted to mark an object as not entirely typical, adding nickel without iron would be subtle but noticeable, a cosmic fingerprint. This idea is intriguing, but requires anthropocentric assumptions. It assumes an advanced civilization would think like us, would value spectroscopy as we do, would find nickel emission significant. Projecting human reasoning onto unknown intelligence is risky. We might be seeing patterns that don't exist, finding meaning in coincidence. Some researchers suggested looking for additional markers, isotope ratios too precise to occur naturally, Molecular abundances too uniform, structural features too regular. Careful analysis of the data turned up nothing conclusive. Isotopes were slightly unusual but within natural bounds. Molecular abundances varied as expected. Structure, to the extent it could be inferred, appeared irregular. If 3I Atlas carries a message, the encoding is remarkably subtle. The hypothesis also raises broader questions. If interstellar probes disguised as comets are common, how many have we missed? How many objects in our catalogues might be artificial? The answer is almost certainly zero or very, very close. But the possibility is unsettling. It suggests the universe might be more communicative, more crowded with intelligence than we assume. That signals might be flowing around us constantly, through channels we don't monitor, in languages we don't recognize, or it suggests nothing at all, because the hypothesis might simply be wrong. This is the challenge of speculative thinking. It's intellectually stimulating. It pushes boundaries. It forces consideration of uncomfortable possibilities. But speculation isn't science until it's testable. And the masked signal hypothesis, as currently formulated, barely crosses that threshold. For now, it remains an idea on the fringes discussed in late-night conversations, mentioned in speculative footnotes, explored in theoretical workshops. Not mainstream, not widely accepted, but not entirely dismissed either. Because the truth is stark and humbling, we don't know. We don't know if 3I Atlas is natural, engineered, or something in between. We don't know if interstellar objects are inert debris or active messengers. We don't know if signals surround us, invisible simply because we haven't learned to see. And in the absence of certainty, imagination fills the void. The facts are extraordinary enough. But the masked signal, hypothesis, whether correct or not, forces important questions. Questions about our methods, our assumptions, our readiness to recognize the unexpected. Sometimes the value of a hypothesis isn't in being right. It's in making us think differently. And by that measure, even this speculative idea serves a purpose. Another speculative framework emerged from a December 2025 conference on interstellar objects. A small group of researchers presented what they called the shepherd scenario, a radically different interpretation of 3I Atlas. The scenario begins with a simple question. What if 3I Atlas isn't alone? What if it's part of a system, a visible component, accompanied by one or more smaller, darker objects that remain undetected? The bright, active object attracts attention, drawing every telescope toward it. Meanwhile, companions silent, non-outgassing, perhaps deliberately dark travel alongside, hidden in the glare or simply too faint to see. It would be a form of camouflage. The bright object distracts. The real payload, whatever it might be, slips through unnoticed. Why would such a configuration exist? In a purely natural context, it's difficult to justify. Binary comets do exist, but they don't exhibit this kind of behavior. They're just two bodies orbiting each other, both visible. The shepherd scenario requires something more: intentionality, design, purpose. But in an artificial context, it makes strategic sense. If you wanted to send something through another star system, without revealing its presence, pairing it with a bright, seemingly natural decoy would be effective. Observers focus on the obvious target. The hidden component passes undetected. The scenario could explain the missing acceleration. If outgassing comes from the bright decoy, but a more massive companion travels nearby, the system's center of mass might not accelerate detectably. Momentum from the outgassing would distribute across both objects, potentially cancelling or minimizing observable effects. Think of a binary star system where one star is much brighter. If you see only the bright star, its motion looks strange, wobbling without obvious cause. Only by detecting the faint companion does the motion make sense. Could 3I Atlas have a companion? Detecting a dark, silent object near a bright coma is extraordinarily difficult. High-resolution imaging, like Hubble provided, might reveal a companion if it were close and large. But if the companion was small, a few hundred meters, across or distant from the nucleus thousands of kilometers away, it would be invisible against the coma's glow. Some researchers revisited Hubble images, searching for faint point sources. A few candidates appeared dim dots, that might be background stars, detector noise, or instrumental artifacts. None were conclusively identified as physical companions. Follow-up observations were considered but never executed, as the object faded too quickly. The radar observation from Goldstone provided one. Constraint. The faint echo suggested a single solid nucleus, not obviously binary. But radar resolution is limited. If a companion existed far enough from the main body, radar wouldn't separate them. So the question remains open. A companion might exist, or might not. Current data can't confirm or exclude the possibility. If a companion exists, what might it be? Naturally, it could be a fragment, a piece broken off during a collision eons ago, now traveling together through space. Such fragments sometimes stay loosely associated for long periods before drifting apart. Artificially, the possibilities expand dramatically. The companion could be a probe, a sensor array, a storage device. It might be dormant, waiting for activation. Or it might be actively observing, recording, transmitting data across the vast distances between stars. This is deep speculation, edging toward science fiction. But the Shepard scenario gained discussion because it offered an explanation, albeit exotic, for behavior that otherwise resists easy interpretation. And there was one detail that lent the scenario faint plausibility: the trajectory. 3I Atlas passed relatively close to Earth, within about 1.7 astronomical units. That's not a dramatic flyby, but it's closer than most random interstellar trajectories would naturally pass. Some researchers calculated the probability of an interstellar object passing this close by pure chance. The odds were low, perhaps a few percent, over any given decade. So either the passage was coincidental, or the trajectory was influenced somehow. If the object or system were capable of minor course corrections during its interstellar journey, it could have aimed toward the inner solar system, perhaps even toward Earth specifically. Why target Earth? If observation were the goal, Earth would be interesting, a planet with life, with technology, with electromagnetic emissions leaking into space for the past century. A probe designed to study inhabited worlds might prioritize systems showing signs of biology or intelligence. Of course, this assumes the probe's creators knew about Earth beforehand. Human radio and television broadcasts have been propagating outward at light speed for roughly a century. Any civilization within that expanding sphere could, in principle, have detected those signals and responded. But the timing is problematic. If 3I Atlas traveled at its observed speed about 30 kilometers per second, it would take thousands of years to cross even modest interstellar distances. The mathematics don't align neatly unless the probe was already en route for other reasons, adjusting trajectory upon detecting our signals. This is speculation stacked upon speculation, leaning heavily on coincidence and assumption. But it illustrates how far thinking can go once the possibility of artificiality enters consideration. Each step seems reasonable individually, but together they build a tower of maybes. The Shepard scenario has its critics, and they're vocal. Many argue it's unnecessarily complex, that invoking hidden companions and deliberate trajectories overcomplicates when simpler natural explanations, however unlikely, remain viable. Occam's razor favors simplicity. But Occam's razor is a guideline, not a law. Sometimes the simplest explanation is wrong. Sometimes reality is more complex than intuition suggests. And so the scenario persists, neither proven nor disproven, hovering in the realm of possibilities. Whether or not a companion exists, whether or not the trajectory was deliberate, the Shepard scenario serves a function. It expands the conversation. It challenges researchers to consider what might be overlooked. It questions assumptions about detection methods and observational completeness. The facts are extraordinary enough, but the scenarios constructed around those facts reveal as much about human imagination as about the universe itself. We observe, we measure, we theorize, but certainty remains elusive. And in that uncertainty lies both frustration and wonder, the endless tension between what we know and what we yearn to understand. While some researchers explored exotic hypotheses, others took a different approach: statistics. Instead of asking, "What is 3I Atlas?" they asked, "How likely is an object like this to exist naturally?" This is a powerful reframing. It sidesteps debates about mechanisms and focuses on probabilities. If an object's properties are statistically improbable, not impossible, just rare, that doesn't prove artificiality. But it does suggest our understanding of natural processes might be incomplete. So how improbable is 3I Atlas? Start with the missing acceleration. Astronomers have studied thousands of comets over more than 2 centuries. Every single active comet, without exception, has shown measurable non-gravitational acceleration when outgassing is present. The relationship between visible activity and orbital perturbation is one of the most robust patterns in planetary science. 3I Atlas violates that pattern. To estimate rarity, researchers examined historical comet data, looking at the distribution of accelerations among active comets. The range is broad. Some comets show strong effects, others weak, but zero isn't in the distribution. Not once. Think of it this way. If you flip a coin 1,000 times, you expect roughly 500 heads. If you get 490, that's normal variation. If you get 450, that's unusual but possible. If you get 0 heads, not a single one in 1,000 flips, you start questioning whether it's really a fair coin. 3I Atlas is the 0 heads. Among thousands of active comets observed throughout history, it's the only one showing this behavior. Now layer in the other anomalies: the apparent lack of detectable rotation, the nickel emission without corresponding iron, the remarkably uniform coma, the stable, unvarying activity over months. Each anomaly, considered individually, might be unusual but not impossible. But all of them together, in a single object. This is where probability becomes uncomfortable. If each anomaly has, say, a 1 in 100 chance of occurring naturally, and if they're independent of each other, then finding all of them in one object has odds closer to 1 in billions. Of course, they might not be independent. Perhaps a single underlying cause, like perfect internal symmetry, produces multiple observable effects. That would improve the odds considerably. But it still requires explaining how such symmetry arose naturally in a 4-kilometer body formed billions of years ago in another star system. The statistical argument doesn't prove anything. It can't. Statistics describe likelihood, not certainty, but they frame the puzzle clearly. 3I Atlas is either extraordinarily lucky, the cosmic lottery winner, or it represents something we haven't properly categorized yet. One researcher attempted a simulation running millions of virtual scenarios of comet formation and evolution. The goal was to see how often an object resembling 3I Atlas would naturally arise. The results were unsettling. Depending on assumptions about internal structure and formation conditions, objects like 3I Atlas appeared anywhere from 1 in 10,000 to 1 in 10 million trials. 1 in 10,000 is rare but acceptable. Over billions of years and countless star systems, rare events become inevitable. 1 in 10 million is different. That's rare enough to suggest either we're witnessing something genuinely exceptional or the models are missing fundamental processes. Another angle involved the interstellar object population itself. Based on 3 confirmed detections in less than a decade, astronomers estimate several interstellar objects larger than 100 meters pass through the inner solar system every year. Most go undetected. If that's true, then over cosmic timescales, thousands or millions of such objects have passed through. Eventually, even 1 in a million oddities appear. This is comforting. It suggests 3I Atlas might simply be the weird one we happen to catch, the outlier, in a vast, mostly invisible population. But here's the counterpoint. All 3 detected interstellar objects have been anomalous. Oumuamua, with its unexplained acceleration. Even Borisov, the normal one, showed subtle compositional peculiarities. Now, 3I Atlas with its missing acceleration. 3 detections, 3 anomalies. That's not a reassuring pattern. Either humanity is incredibly unlucky, consistently catching the strangest visitors, or interstellar space genuinely contains more oddities than theory predicts. Both possibilities are unsettling. The statistical argument leads to an impasse. Natural explanations require accepting a series of low-probability conditions occurring simultaneously. Artificial explanations require accepting something even less probable that we've detected evidence of. Technology from another civilization. Which is more unlikely? A cosmic coincidence or cosmic company? The answer depends entirely on assumptions we can't verify. How common is life? How common is technological life? How long do civilizations last? How often do they send objects into interstellar space? We don't know any of these numbers, so the calculation can't be completed. The statistical argument circles back to uncertainty, proving only that we're dealing with something genuinely unusual. One researcher, speaking at a conference in early 2026, framed it simply, "We've observed something that challenges our models. Every explanation we've proposed, natural or otherwise, requires accepting premises we can't fully justify." That's where we are, suspended between possibilities, unable to choose definitively. The facts are extraordinary enough, but the statistics force us to confront just how extraordinary they really are. Not impossible, not definitive, just improbable enough to keep us wondering. And as 3i Atlas faded into the darkness, that wonder remained. The numbers couldn't answer the question, they could only sharpen it. So here we are, at the end of the investigation, at the boundary of knowledge. 3i Atlas arrived in March 2025, a faint point of light caught by the Atlas survey in Hawaii. For 9 months, humanity watched it. Hubble, JWST, the world's most powerful telescopes, all trained their instruments on this visitor from beyond. Thousands of observations, hundreds of spectra, millions of measurements. And after all that effort, after all that data, after all those sleepless nights and heated debates, we still don't definitively know what we saw. The object outgassed like a comet. It had a coma, molecular emissions, all the signatures of active sublimation, but it showed no measurable non-gravitational acceleration, the recoil that every other active comet in history has exhibited. It was as if the laws of momentum simply didn't apply. Its coma was unnaturally uniform. Its activity was unnaturally stable. Its chemistry was subtly wrong nickel without iron, a signature that doesn't quite fit natural expectations. It showed no clear rotation, no outbursts, no chaos, just steady, measured behavior that seemed almost controlled. Natural explanations exist: perfectly symmetric outgassing, unusually high mass, exotic internal structure, favorable geometry. Each explanation is possible. Each requires specific conditions. Stack them all together, and you get something that works mathematically but feels forced. It's like solving a puzzle by trimming pieces to fit rather than finding pieces that naturally belong. The alternative explanation that some aspect of the object involved design, purpose, technology faces even steeper challenges. No radio signals, no obvious structures, no smoking gun that screams artificiality. Everything observed can, with effort, be explained naturally. But can be explained isn't the same as is, easily explained. And that's the space 3i Atlas occupies, not impossible naturally, not obviously artificial, just uncomfortable, ambiguous, resistant to easy categorization. Some researchers have embraced the mystery, arguing that ambiguity itself is valuable. It expands the conversation, challenges assumptions, forces consideration of possibilities previously dismissed. Others see ambiguity as a call for patience. More data will come, more interstellar objects will be detected. Patterns will emerge. What seems unique today might prove common tomorrow. Both perspectives are valid, both are honest, both acknowledge that right now, in this moment, we simply don't have the answer. The silence from SETI added another layer. No technological signals, no transmissions, no emissions that couldn't be explained by passive thermal processes. If 3i Atlas carried technology, it was either inactive or designed to be undetectable. That could mean it's natural, or it could mean we don't know what to look for. The trajectory brought the object relatively close to Earth, closer than random chance might suggest. Was that deliberate, a targeted approach, or just coincidence in a universe filled with coincidences? We don't know. The nickel anomaly, The stable activity, the missing acceleration, each is a thread that, when pulled, doesn't quite unravel the mystery. It just exposes more threads, more questions, more uncertainty. And now the object is gone, receding into interstellar space at more than 30 kilometers per second, heading back toward the constellation Eridanus. In a few decades, it will be beyond the Kuiper belt. In a century, beyond the heliopause. And then, silence. All we have left is the data, the archive, the observations that will be studied for years, perhaps decades. Future researchers with better tools and deeper understanding might extract insights we've missed, or they might confirm what many suspect, that 3I Atlas will remain one of astronomy's great, unsolved mysteries. But here's what the object did accomplish. Regardless of what it was, it challenged us. It challenged our models of cometry physics. It challenged our assumptions about what's possible naturally. It challenged the boundaries between skepticism and curiosity, between rigor and imagination. It forced astronomers to confront uncomfortable questions about how we investigate the anomalous, how we communicate uncertainty, how we balance the extraordinary nature of observations with the extraordinary standards required for extraordinary claims. And it reminded us that the universe doesn't owe us easy answers. That mystery is the natural state. That sometimes the most honest response to a question is, we don't know. 3 words that are difficult for science to say, 3 words that feel like failure, but 3 words that might be the most accurate description of where we are. We don't know what 3I Atlas was. We know what it did outgassed without accelerating, maintained impossible stability, defied expectations at every turn. We know it challenged us. We know it expanded our thinking. But we don't know what it was. Was it a cosmic oddball? A statistical fluke? The 1 in a million configuration of ice and rock that happened to drift through our solar system at exactly the moment we could observe it? Or was it something more? A visitor carrying traces of design, an object that crossed the boundary between natural and artificial in ways so subtle we couldn't quite perceive it. The data doesn't settle the question, it only sharpens it. And perhaps that's the most profound lesson 3I Atlas offers. Not answers, but the humility to recognize when we don't have them. Not certainty, but the courage to sit with ambiguity. Not resolution, but the acknowledgement that some questions might remain open far longer than we'd like. Another visitor will come. Perhaps next year, perhaps next decade. It might be similar to 3I Atlas, or radically different. It might resolve these mysteries, or deepen them further. Until then, we're left with wonder, with data that doesn't quite fit, with observations that resist interpretation, with the uncomfortable awareness that we might have witnessed something genuinely unprecedented, and we're still not sure what it means. The facts are extraordinary enough, but the answer remains just beyond our grasp, receding into darkness along with the object itself. And in that darkness, a question lingers. A question that won't fade as easily as the light from a distant coma. A question that will follow astronomy into the future, shaping how we look at the next visitor and the one after that. Are we looking at a cosmic oddball, or our first confirmed artifact? The universe isn't telling, not yet, maybe not ever. But the question is real. The observations are real. The challenge to our understanding is real, and whether 3I Atlas was natural or something else entirely, it has left us changed. More uncertain, perhaps, but also more curious, more willing to question, more prepared to consider possibilities that once seemed beyond consideration. The object is gone, but the mystery endures, and somewhere in the vast darkness between stars, another wanderer is already on its way. If you followed this investigation from beginning to end, if you felt the tension between skepticism and wonder, if you're left with questions that won't quite let go, you're not alone. We want to hear from you. What do you think 3I Atlas really was? A bizarre natural object that happened to hit every statistical longshot, or something that challenges the very boundary between natural and artificial? Drop your thoughts in the comments below. And if you want to follow future investigations because another visitor is coming, And it might be even stranger, subscribe to this channel. Hit the notification bell, because when the next interstellar object arrives, we'll be watching. And we'll bring you every detail, every mystery, every moment of discovery. The universe is stranger than we imagine, and the story is just beginning. Thank you for watching, and keep looking up.